Check in. Good. Screen. Let's go back to our notes right here. Oh, first let's go through the syllabus, right? Okay, we are writing here. Today is the 11th. We're still doing matter waves 1. The book, which is chapter 38. Which is chapter 38. Let's put that here. And it's going to be version 11. And later on, you're going to have lab number 6. Notes. So what you have to know, one, I posted the correction of reports of labs 3 and 4. I uploaded, right? Of reports of lab 3 and 4 reports. Okay, we are still doing the photoelectric effect. That's matter waves 1, chapter 38. Let's see if we can finish it today. Okay. And so far we've covered what? I prefer to start with chapter 38.4. And that's what we did, chapter 38.4, and we start covering 38.1, 38.2. Okay, that's what we did so far, and let's continue with that. Remember, here you go. Going back right in here, right? What we calculated here, I'm going to copy and paste it, this example, so you can refresh your mind. We had this example that had a photon of frequency 400 terahertz. And then I will, according to Einstein, right? What is its energy, right? And went ahead and calculate H times F. We got this value here, 1.65 electron volts, which is nothing but 1.65 times the charge of the electron, which is around 1.6 times 10 to minus 19. And then we revert back it to joules. Charge of the electron times volts is equal to joules. Okay, that's how you convert electron volts to joules. Okay, and the idea that we must now start having about the electron is that not the electron, must have about the photon, is that it's not just behaving like a wave. Okay, it's behaving like a particle, as a point particle. That's why we call it a photon. A photon is a particle of light. And we can even determine what's the intensity of a single photon. There are people who say out there that the human eye is sensitive to 3 photons. You must have at least 3 photons incident in your retina for the brain to pick up the light. Okay. And instead of, like I said, instead of thinking of the light as a wave that little by little transfer energy to electron, and eventually that accumulated energy of the electron of the electron is gonna eject it from the metal. Now the current idea of the photon is that it is a point particle that's undergoing collisions with the electron. And there's plenty of evidence to support this interpretation. Because when we have the photoelectric effect, the electron is almost instantaneously ejected from the metal, which correlate with the idea that we have a collision between a photon and an electron. Okay, so instead of imparting energy little by little to the electron, the photon of light would collide with the electron, emitting the electron almost instantaneously. That's what we observe experimentally, and this experimental evidence lends support to the fact that the photon is colliding, is a particle that's colliding with the electron. Okay, now we saw the table of the work function of many metals, right? Remember? Recall that the work function of most metals lie in the range of 2 to 6 electron volts. So obviously, the red photon doesn't have enough energy to eject the material that has the least value of the work function. The least value of the work function. Okay? So that's why we need to use UV light. That is why we need to use most of the time UV light. UV light has most of the energy. And that's why, Hertz himself observed that UV light was the one that was generating the photoelectrons. And then you can go ahead and perform. You can go ahead. Let's go back to that table of work function. Just as a work function of metal, and then we're gonna go to Wikipedia. Work function right in here. Oh, here you go. That's the one, right? So pick up, a very good exercise that we can do to get familiar with this idea. Get more familiar with this idea. In order for you to become familiar with the idea, that we must do some work on that. Generate a table of, let's say, 10 of those elements. Just as an exercise, it's not extra credit, it's not homework, just as an exercise for you to understand better the concept of the work function. Choose 10 different metals and find out what is the wavelengths of the photon, what is the, not the minimum, what's the minimum, find out what is the minimum frequency. If you're looking for the minimum frequency, then we also be looking for or the maximum wavelengths of different photons to eject a photoelectron from the metal surface. Okay, so you'll be doing something like that. I'm just gonna give you, again, it's not for grading, but it's important that you do. You can do that with Excel to become familiar with it, with this idea. So we're gonna have the metal here. We're going to have the work function, right, in the vertical. The third vertical column is going to be the minimum frequency of the photon and the maximum wavelength of the photon. That. Oh, and by the way, let's put another column here, and then you're going to say which type of light which type of electromagnetic radiation is, right? So here you go, element, right? That's the first one. It's going to be iron, it's going to be lead, it's going to be gold, it's going to be zinc, and so on. Choose 10. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. You can do that in Excel. Okay, element, work function. Okay, the work function is going to be in electron volts. Next is going to be minimum frequency. Next is going to be maximum wavelengths. Max wavelengths. And I'm going to change here to symbol. And the next one here, what's the light type? Is it red? Is it blue? Is it green? Is it yellow? Is it UV? Okay. And we have, let's get beryllium from our table. Beryllium is 4.98 electron volts. That's the work function of the electron. This is just one example, right? And here goes. I'm gonna even do it in my spreadsheet here. Those Excel spreadsheets are really good, very good software to have around. Some professors discourage you from using those things. I don't know why. It's a good time saving. Here we go. Freeze panes, we go. So element, right? Work function. I'm gonna abbreviate work function by WF. The unit is the electron volt. And WF for work function, right? The F stands for function. Subscript, italicize. The next one is going to be the minimum frequency. The minimum frequency. Oh, what did I do here? Let's see. Interesting. It's not supposed to do that. So let's do that again. Subscript, the minimum frequency required. And this minimum frequency is going to be in hertz. Whether it's going to be in terahertz, that's a different story. Terahertz, megahertz, gigahertz, that's another story, right? The next one is going to be the wavelengths. I'm doing some of the work for you here, so symbol. And it's not going to be the minimum wavelengths, it's going to be the max wavelengths, because there is an inverse relation between the frequency and the wavelengths. The next one here is the color of wavelengths, right? Color of the wavelengths. And you're going to need the velocity of the light here too if you want to make the conversion. 1, 2, 1, 2, 3, 1, 2, 3, right? Everything must be done in terms of SI units, meter per second. Oh, it's not going to be hertz here, it's going to be meter. Okay? And remember, I'm going to do just one, and then you choose 9 other, and then you do it. And you find out what's going to be the color of this wavelength. Okay, so in the case of the work function is 498 electron volts, right? So if you want to know the minimum wavelengths, you have to get the work function and divided it by the Planck's constant that I'm going to put it right now. I'm going to write right now. Here you go. Put a dollar sign here. Planck's constant, joules second, right? Joules second, Planck's constant. Planck's constant. That's gonna be. But there is also another way of writing there's a way to write the Planck's constant joules second, right? 6.6 times 10 to minus 34. That's one way of writing the Planck constant. And there is another way of writing the Planck constant. Planck constant in electron volts. In electron volts, okay? Electron volts second, that's going to be H electron volts second. 4.1357 e to minus 15. It's a matter of multiplying by that constant, related to 19, right? Minus 19. If you sum this one with minus 19, you get minus 34. Okay, minus 19 is the power of the electric charge. That's one way to do that. So here you go. And now that I have it here, let's see. Joules per, yeah. We get this value here for the frequency. And then we have to get the value for the wavelengths in meter. That is something, what's going on here? C, 25. Let's see here. That looks like something is wrong here. Let's take a look. Notes. Not this one. Lambda, right? Lambda times f is equal to the speed of the light, right? So the speed of the light, the wavelengths must be equal to c divided by f. So it looks like I inverted the equation, right? Gotta be watching for those things. Is c is the inverse, is the speed of the light divided by the frequency. I did all the opposite. I did the frequency divided by the speed of the light. And now minus 26. Let's see here. Oh yeah, what am I doing here? That is yeah, I used the wrong one, right? This work function is in electron volts, right? So I must use the H in electron volts. Otherwise, I'm gonna get the wrong, incorrect result. Okay, so it works like that. Going back to the equation here, it's always good to do the equations properly so you don't make this type of mistake. the work function, right? And it's gonna be h times the minimum wavelength, the frequency. The minimum frequency, like that. And then we divide the work function by h, but let's not forget this work function is being given in electron volts. Consequently, the h must be in electron volts as well. So we have to use the h in the proper unit. And now it looks like we're getting the right value for the frequency. Okay. I want to convert the wavelengths in nanometers because the wavelengths in nanometers is easier to visualize. In order to write that down in terms of nanometer, you gotta multiply by E 10 to the 9. It was in meter, now it's in nanometers. So we're talking about 249 nanometers, which is in the UV, ultraviolet. Those, you can buy sources of these wavelengths. They are rather expensive. LEDs, they make LEDs of the UV. Okay, they are around like $500, just a little LED. Some time ago, I bought some of those, not at these wavelengths, but at longer wavelengths. And they also have UV LEDs that they use in those places that you get a ton, right? They have this booth that you go, they put UV LEDs all over the place. In this case, the UV LED that they have is 280 nanometers, a little bit longer than that. And you can buy those for pretty, for a very good price because they mass manufacture that, because there is a bunch of tanning salons out there. People buy those 280 nanometers LEDs, and because they can mass manufacture that, so the price can come down. So instead of paying $500, you pay like $20 for each LED, but you have to buy in bulk, in large quantities. I want to buy one of those for my experiments. Number. Okay. And then you go do for the rest, right? You do for the rest. So you can 1, 2, 3, 4, 5, 6. Would be better if you have 6 columns. And I'm gonna correct my notes here. Instead, I had 1, 2, 3, 4, 5. Right? Let's do 6 instead. And that should be in hertz. Here, you start with meter, and then you convert to nanometer. Then you convert to nanometer. Here you go, nanometer right in here. And I'll do that. Work function, we got that, don't forget we got that from Wikipedia, right? WF, work function in electron volts. Now we saved on space here, on the width of the column. Play a little bit more, is that make sure it looks nice, right? So if you do that in Excel, you're going to do that much more quicker. And then you just come up with just a single equation. If I want to do the next one, let's go work. The next one, I want to do, let's say, 5.9 selenium. Selenium is going to be even higher, longer wave, higher frequency selenium. Loss of energy here. And then all I have to do here, let's make sure I got everything. This one, yeah, this one I gotta put that $sign here. This one doesn't need a $sign, right? And now we can click and drag. The equation seems to be correct. Oh, why are we getting 0 here? Okay, I think I know what I need here. Yes, here I made a mistake again. That's the debugging, right? That's the debugging process. I put the dollar sign in the wrong place. The dollar sign should go to G because that's the constant that I want. What about here? Do we need a dollar sign? No, we don't need a dollar sign. Here you go. And now we get 210. 210 nanometers, also ultraviolet, okay? They do sell a 210 nanometer LEDs out there in the market. I'm eager to buy one of those. But for now, I'm just working with 300, 310 nanometers. And all those values here, they are constant. And then you can do the rest, right? You can do the rest for 8 more, just for practice purpose. You spend some time here, you end up organizing everything better, right? That's the table. That's say 11 elements. Like that. Okay. If I get the other one, let's see, the rubidium 2.261, 2.261 on the other extreme, right? Rubidium. Yeah, RB. So we go ahead and calculate that. And that's around 549 nanometers. 549 nanometers, I believe it's in the green. Let's take a look. That's my guess. That's my guess. Even I don't memorize those things. But let's go. Green wavelengths. Wavelengths of green light. Right? Oh, 400. Oh, 400, 450. Okay, so it's not green. It's 549 longer wavelengths. What's next after green? Let's see. Close to green must be the yellow of yellow light. 570. 570. We have 540. So it's between the green and the yellow. I'm getting, 540. Let's go back here. Or it might be, let's see. Wavelength green light is, oh, no. It's just a question. Around 550. Okay, so going back here, around 550. Yeah, I was right here. Primary wavelength, green has a primary wavelength between 549 and 570. So it's right, 550, green color. So it was right in the first take. Okay, and so on, right? Let me save that here. And now let me give you an idea of how we can perform this photoelectric effect, okay? There is a, oh, by the way, I have to say that, very important. What we calculated was the minimum frequency required to eject an electron from the atom in this, under the circumstance, right? Under the circumstance, the electron would be ejected from the, not the atom, but from the metal, better, would be ejected from the metal and would be hovering above the metal's surface. Okay. If we increase the frequency, then the electron would be imparted a kinetic energy, a velocity. Okay? So not only that, if we increase the frequency, right, above this minimum, then the electron would be flowing, would be moving with a given kinetic energy. Can you picture that? Okay, and now we generate a current. And then a current would be generated. Current will be generated. The electron is moving, then we must have a current. Can you picture that? So the actual equation ends up being the following. The genetic equation, right? Ends up being HF. Here you go. I'm gonna use that here. HF. Now we're not dealing with the minimum frequency, but any genetic frequency above the minimum. By conservation of energy, we must write down, HF is the work function plus the maximum value of the kinetic energy of the electron, of the photoelectron. I'm gonna write this guy on the left side. Like that. For the case in which F is greater, right, than F minimum. That's what we have to have in mind. And it's something like that, right? HF greater than 5, we have an electron flowing. HF equal to 5, the electron just hover above the metal. In general, is UV light, okay? In general, is UV light. And by the way, now you understand what is the reason, right, that X-ray and gamma rays are called ionizing radiation. Make sense? Now you understand why X-ray and gamma ray are called ionizing radiation, because it can ionize substances, it can ionize materials, it can extract electrons from a material, just like UV light does. But of course, X-ray and gamma rays have a much higher frequency than UV light, and it's dangerous for human life if you become exposed to it for a long time, right? By the same token that UV light is also prejudicial to human life. So if you want to picture how we can conduct a photoelectric effect, just think about your regular circuit, okay? Just think about your regular circuit. I'm going to keep on switching back and forth between my notes and this slideshow, okay? If you want to know how you can perform a regular photoelectric experiment, come on, just visualize your regular circuit. Okay, so the situation is like that: a battery with a resistor in a closed circuit. A closed circuit. Producing a current. Okay, that's what we have. Here you go. Battery, resistor, and then we can also put an ammeter here to measure the current. Ammeters are very cheap out there. You can buy them. Plus an ammeter. A battery is a resistor and an ammeter. To measure the current. Okay, a battery to generate the current, a resistor to moderate the current, otherwise you can burn out your battery if you don't have a resistor in there, and an ammeter to measure the current. All of that in a closed circuit. All of that in a closed circuit. All of that in a closed circuit, producing a current. It's very important that you can visualize this type of experiment. It's even more important if you can yourself come up with a circuit like that at home or anywhere else that you would have access to those elements. They're not expensive, okay? You can use a 9-volt battery. You can use resistors that cost almost nothing. Ammeters, they cost you, start costing at $10, $15, $30. And then if you want a fancy ammeter, then you're going to be paying $300, $3,000, depending on how fancy the ammeter is. But you want to stay away from those expensive ammeters, right? Just for understanding, to visualize what you have here. So what do we do next? What do we do next? You remove the resistance. Remember, I'm not short-circuiting here, the circuit. I'm just removing and leaving the air in between those two leads, okay? So in the next step, remove the resistor, leaving just the air between the leads of the metal wire, okay? Remember, we want to visualize how we can perform this photoelectric experiment. That's the simplest way I have figured out how you can do that. Once we remove the resistor, something interesting happens. Not only the current goes to zero, right? Because the circuit is no longer closed. Now the circuit is open. Now we have an infinite resistance between those 2 points because air is a dielectric. Let's not say infinite, let's say a very large resistance between those 2 points. And when you have something like that, you're going to have an accumulation of charges at the end of those wires. Okay? Very important. You have to visualize that too. You will accumulate electric charges, would be positive charges here and negative charges here. Those negative charges are in contact with the negative terminal of the battery. The positive charges are in contact with the positive terminal of the battery. And when you do that, we have an electric field formed between those 2 points, okay? Here's the source of the electric field. Here's the sink of the electric field. We're going to have this complicated feature. So let's go back to our remove the resistor, leaving just the air between the leads. The current goes to zero because air is a dielectric, because the air between the leads, is a dielectric, right? With a very high resistance. 4, there is an accumulation of charges at the leads of the wire. Positive charges facing the positive pole, right, of the battery. There's a better way of the positive, let's leave a pole for now. Negative charges facing the negative pole of the battery. Okay. With this accumulation of charges, with this, we didn't get at the photoelectric effect in there yet, but we're getting there. With the accumulation of charges at these leads, an electric field is formed, right? And then we do something else. We go ahead and install a plate in there. You're familiar with that device, right? A very large metallic plate. A large metallic plate doesn't have to be very large. On the two ends, I'm gonna even remove this charge for now because there is a time lag before the charge, right? In those plates become charged. I can put negative and positive there at those leads of the wire. Here you go. Then here you go, this lead here, the lead of the wire, and eventually all those charges flow to those plates, forming a capacitor, a parallel plate capacitor. We are almost there. We are almost there. So let's, in the next step, connect a plate, a metallic, a conductive plate at these leads. Okay. Soon afterwards, the plates will become charged. Okay, soon afterwards, the plate will become. We still have a zero current. Remember, we still have a zero current. There's no current flowing here. Okay, soon after, the plates will become charged. Remove the resistor, bringing the current to zero. Let's put it here, bringing the current to zero. Okay. The current is zero because the air between the leads is a dielectric with a very high resistance. There is an accumulation of charges at the leads of the wire, right? The current is still zero. Soon after, the plates will become charged. And now our photoelectric experiment is about to start. But before, we know that a uniform electric field is formed. A uniform electric field is formed between the plates, right? Step by step, starting with something familiar until we get to the point where we can see the new effect. Now you get your UV light, okay? Remember, this metal has a work function, right? It's trapping those free electrons, those valence electrons in this metal. Depending on the metal, the work function is more or less, anywhere between 2 electron volts to 6 electron volts. You shine a UV light. If the UV light has a frequency high enough to eject the electrons, it will eject. So next step, shine a UV light in the negative plate. Remember the negative plate, negatively charged plate on the negatively charged plate. Okay. But now the situation is a little bit different than what we had discussed before. Now we have this electric field right in here. All right. We have this electric field that's going to add some energy to my electrons. Once the electron, the photoelectron, is ejected, suppose that UV light is just there enough to make the electron hover at the surface of we call that the emitter, right? The emitter. this electric field will accelerate the electron towards the positive plate. Okay? Make sense? Okay, so shine a UV light on the negatively charged plate. If the frequency of the UV light is high enough, a photoelectron will be emitted from the surface of the plate. Furthermore, if HF is equal to the work function, right? Work function, the photoelectron will momentarily hover above the emitter plate. Okay, remember the electron is very light. Because the electron is very light, it's not going to sink due to the force of gravity. Okay, it's not going to sink. The electron has such a small mass that it doesn't feel almost any gravitational force compared to the electric force that are at stake here. Will momentarily float. Okay, and however, the electric field of the plates will accelerate the photoelectron towards the positive plate. That's the emitter, and then this is the collector. That's what we call the emitter and the collector. Make sense? Right? So we have now this equation, right? Initial kinetic energy plus initial potential energy. And now we're talking about the potential energy of the electric field is equal to final kinetic energy plus final potential energy. So we end up with this equation that you see right in here. Okay, and that's the picture that you must have. Once the electron reaches the collector, it's going to be injected in the circuit, and your multimeter will be able to measure a current. That's the current, that's the direction of motion of the electron, right? The photoelectron. But the actual current that we measure is in the other direction, which is the motion of the positive charges. So that's the idea. That's the type of experiment, that's the type of thought experiment that you must have in mind. Okay. Then we can perform the experiment in a different way. There you go. We can perform the experiment in a different way. We can shine light in the negative plate, or we can shine light in the positive plate. Now it's going to be a little bit more difficult for the electron to generate a current, right? So let's finish my notes here. There's the positive plate. When the photoelectron collides with the positive plate, we call that the collector. Okay. A photo current is generated in the circuit. Okay. Photocurrent is generated in the circuit. Photoelectron, they don't want to be separated by that dash, right? Here you go. Now let's see how you can do the experiment in the other way. Now, what if I shine the light? Those are the type of experiments that Hertz were doing. Okay, remember the spark gap that he was generating there in his experiment that we mentioned? The difference is that Hertz was not using a battery, but he was using a AC source. He was using a generator. Okay, now here you go. We go ahead, shine UV light in the positively charged plate, right? If the frequency, if the energy of the light is equal to the work function of the plate, the electron is going to be generated, will momentarily hover over the plate, and then it's going to be attracted by the positive plate again. That's what's going to happen. Okay? That's what's going to happen. Make sense? And now, if the frequency is high enough for the electron, if the kinetic energy imparted by the UV light is high enough to impart the kinetic energy to this electron, here the electron is going to move uphill. Hopefully, the energy is going to be enough to collide against this negative plate, right? Here you go. Here's the electron moving from the positive plate. He is slowing down. He has a negative acceleration. Okay? And it may, produce a current in the other direction, a photocurrent in the other direction. Photocurrent. And your ammeter will be able to register that, right? The electron is going to be collected by this plate, but wait a minute, these negative electrons are going to repel this photoelectron. And it's easier for the photoelectron to follow this circuit here instead of being re-ejected to the air. You won't be re-ejected to the air because it requires more energy to eject the electron to the air than to follow the circuit. That's the type of experiment that you have to keep in mind, okay? And we can perform this experiment. We can perform the same experiment by shining UV light, shining UV on the positively charged plate, okay? Remember, because it's a positively charged, it's not just, it is a positively charged plate, but it's an excess of positive charges. It still has some electrons in there. Although it is a positively charged plate, it still has some electrons there inside the plate, right? When we say the plate is positively charged, we mean that the plate has an excess of positive charges. In other words, the plate has an excess of positive charges, right? Some electrons. In other words, the plate has an excess of positive charges compared to the negative charges. Okay? That's what And then you can use conservation of energy to figure out what would be the energy, the kinetic energy of the electron, okay? Any questions? Am I missing anything here? Nobody sent me a message, that's good. And then we're gonna go for something else that's a little bit more complicated, but it's a very challenging and interesting problem. But before we do that, let's take attendance. Lecture today is the 11th. Sydney Duckworth. Let's see. Hi, Sydney. Looks like Sydney is away from her computer. I'll put a star here. Amy hand. I don't see Amy here. Okay. Sydney. Okay. Thank you, Sydney. Andy, he. Are you there, Andy? Okay, I'm gonna put a star here. Alex Hernandez. Thank you, Alex. Oh gosh, I keep on doing that. I don't know why. Tartak. Hello, Sartak. Sartak is in my list, but I don't hear from Sartak. I'll put a star. Basilio Lopez.
Here.
Thank you, Basilio. Jeshuan.
I'm here, Professor.
Thank you. Alex Hernandez is here. Zaid, are you there, Zaid? Good. Zaid raise his hand. Sumana? I don't see Sumana. Nope. No Sumana. Alisa is here already, right? Alisa, thank you. And Kartika? Thank you, Kartika. Mary? Shukurian. Thank you, Mary. Raymond Silverman? Thank you, Raymond. Ashley Thai?
Here.
Thank you, Ashley. Kirakus? I don't see Kirakus. Maybe, Kirakus. Yeah, I don't see Kirakus. Alexis Madrigal. And I don't hear from Alexis. That's Andy just replied to me. And now Amy just came, right? Amy, are you there? Okay, and another opportunity for Sartak. Are you there? Sartak and Alexis Valley. Okay, 2 students that didn't reply. Let's 14. Yeah, we have 14 here. Save. Any questions before we proceed, right? Before we proceed for our break? What we're going to see next, I'm not gonna start yet, just to break. After the break, right? After the break, we will cover the Compton effect, which is related, by the way, which is related to the photoelectric effect, provide further evidence of Einstein's interpretation of the photon being a particle. Okay. Let's take a quick look here. The book. This one, because that's what I want. Photons, momentum, Compton scattering, and light interference. Okay, that's what we're going to be doing. We did part of that. Okay, we'll see light interference, photoelectric effect we covered, and the quantum of light. Okay, this idea of the quantum of light is very closely related to the idea of beatings that we saw in light. Okay, you're going to see that we saw in waves, sound waves, even light waves has this beating effect, and we are going to revisit beating here because it's closely related to the quantum of light. Okay, so don't forget to review your notes and break from 9:05 to 9:20 a.m. Okay. So I see you in 15 minutes. Compton effect. Okay. So let's talk about the Compton effect now. So let's see the timeline, right? Let's see the timeline too. Here you go. 1900, Max Planck. The idea, he introduced the idea of the quantized energy of the microscopic simple harmonic oscillator. Quantum mechanics deals with the microscopic world, okay? Remember that. Yeah, let's see. What about Einstein, right? Photoelectric effect. Okay, let's see. Model Einstein's model is 1905 Einstein. 1905 Einstein published a paper advancing the hypothesis that light energy is carried in discrete quantized packets. What discrete quantized packet means, it means that it behaves like a particle. But there is more to it. There is more to it. And this idea, discrete quantized packets, is closely related to the phenomenon of beating that I explained to you. And you're going to see further down what exactly it means, what the phenomenon of beating exactly means, not just two different frequencies. We did the phenomenon of beating for two different frequencies, right? But what if we add not two different frequencies, but 3 different frequencies, 4 different frequencies, 5 different frequencies. If we do something like that, that wave that spread out throughout the whole spectrum, throughout the whole position, start to become narrower and narrower in space. It start to become a package or a packet, right? A package of waves, localized waves, like a little pulse. And we're going to see that later on. 1905, Einstein. Einstein proposed an explanation, right, to the photoelectric effect, which, by the way, won him the Nobel Prize in physics. Then we have other people in between. I don't want, there's Robert Millikan too. He did a very nice experiment. He won the Nobel Prize in physics. He did a very nice experiment on the electron. He managed to measure the Planck constant in a very accurate fashion using the photoelectric effect model, right, by Einstein. And then in let's take a look here at the Compton effect. I'm looking at it's closely related to Compton. Yep. So my notes stated that 1923, Holly Compton and Peter Debye carried independent experiments. Remember, there are more people here in between, right? I'm not fighting everybody. There was even a guy that was a Nazi German. This guy was a fervent Nazi supporter, colleague of Einstein, and his name was Leonard. You know, if you watch that TV series, you know, the TV series that I mentioned, they dramatize the interaction between Einstein and Leonard. So he was vehemently against what he called the Jewish physics of interpretation, right? And the irony, okay, and they mentioned that in the TV series. I'm trying to remember. Let's see, Leonard. Let's see here. He was a guy that studied the photoelectric effect as well. And because he was a Nazi, okay, he thought of Jewish people being feared, right? And he thought that Einstein's idea was completely wrong. Leonard, let me try Leonard here. I'm trying to remember. Oh, Philip Leonard. That's his name. Okay, Philip Leonard. Philip Leonard. He was a student of Hertz. It was between 1886 and 1902. Okay, Philip Leonard studied the photoelectric effect in detail, investigated, right? Not studied, but investigated the photoelectric effect in detail. So I'm going to put him fervent Nazist, right? Fervent Nazist. In detail. Nazi. Fervent Nazi. And by the way, Leonard was a disciple of Heinrich Hertz. And the irony was that the main work of Leonard himself, right, which was on the photoelectric effect. You know, Einstein won the Nobel Prize on that same photoelectric effect that Leonard was investigating. So that was the citation that the Nobel Prize committee made, this explicit citation. And Leonard must have got really mad about that, right? Because his specialty was on the photoelectric effect. So that's the more or less the historical background. Though 1923, Holly Compton and Peter Debye carried some independent experiments that confirm the corpuscular nature of the photon. Remember, experiments are very important. You know, if you want to make sense of nature, it's not enough to just provide theories coming up with theoretical explanations. You have to perform experiments as well. Millikan was one of this, was a very good experimenter. Einstein, not so much. Einstein was more like a theoretical guy, but he had a very good intuitive idea of how the cosmos, of how the universe works. Hertz, you know, Hendrik Hertz was an applied physicist, applied scientist too. And, you know, as well as other people like Thomas Edison and Marconi, right? But let's study these experiments performed by Compton and Debye. Let's see how it looks like, right? I have an illustration here. Okay, he had this source of electromagnetic waves, an X-ray source. Okay, X-ray source has very high frequency, much higher than the UV light, much higher than the ultraviolet light. And this X-ray source emits photons of X-ray. The energy of this X-ray is given by the wavelength times the Planck constant. And then if you use Einstein's theory of relativity, you can find out that the photon also has a linear momentum. Remember that equation that we derived, right? Remember that equation that we derived in relativity? I'm going to spell that out for you in case you don't quite remember that. Here you go. I'm going to write that for you. It's like that. Notes. Recall special relativity result about the net energy, right? About the relation between net energy and linear momentum. We had that relationship of E squared, E squared, right? What's going on here? Okay, E squared is equal to m naught c squared. M naught means the rest mass, right? Plus, oh, by the way, it's square here as well. Plus c squared, E squared. Okay. If we are dealing with the photon, which has a rest mass of 0, the above equation reduces to, right, an equation that relates the energy of the photon with linear momentum, like that. E equal to Cp. Okay. And P equal to E sub C. E sub C. And by the way, now Einstein told us that E is going to be equal to what? HF, right? And we can go back to our drawing, to our illustration here. Here you go. The energy of the photon is equal to Planck's constant times the frequency, and let's say the initial, and let's say this is called the initial also energy of the photon, right? Initial energy of my system, and the linear momentum of the photon is also given, is related by the frequency of the photon, HF divided by C. So what was the experiment that those guys performed? There's more to it. There's more components here. I need you to picture that in your mind. They came up with a metal plate. Easy enough, right? No problems here. Visualize what they have. Also, no problem about visualizing the X-ray source, right? Anybody has taken X-ray, has been imaged by X-ray, by an X-ray machine, right? Many hospitals have that. To make a X-ray picture is very inexpensive. Okay, and now we have this X-ray photon that is going to be incident in this metal plate. Okay, and what did they observe? They observed that, just like in the photoelectric effect, that this X-ray photon generates a photoelectron. I should have put photoelectron there. The metal plate has several electrons there, has positively charged particles as well, but the positive charged particles are much more difficult to extract from the metal. So what this X-ray photon can do is to extract an electron. Okay, and this electron, let's say it is emitted at an angle phi with a given kinetic energy. Okay, so here you go. The electron has both, the photoelectron has both a linear momentum and a kinetic energy. And on the top of that, what did they observed? They observed that this X-ray photon is scattered by this metal plate. It doesn't fly through the metal plate. It's somehow the direction of propagation of the X-ray is somehow interfered with, okay? And now we have the following. But by the way, when we mean that the X-ray was scattered, we mean that the frequency of the X-ray changes as well. That's what the scattering effect is all about. It's a change in the wavelengths. It's a change on the frequency of the photon. Every time that you have a scattering wave, a scattered photon, we have a change in the wavelength, just like the blue sky, okay? Light coming from the sun is scattered by the atmosphere. Most of the light of the sun is in the yellow region, but there is some UV light there too. And that spectrum of colors of the light of the sun is scattering into is scattering the blue color, is converted into a blue color. Okay, so that's what the scattering phenomenon is all about, is the change in the frequency of the wavelengths of a radiation, of an electromagnetic radiation. So that's what they observed. Okay, and that's the linear momentum, right? And now with this simple model, we can figure out whether it makes sense or not. Simple model will try to figure out whether it makes sense or not, okay? And what they did, they used Einstein's theory to figure out whether this thing makes sense or not. And they also use conservation of energy. They use conservation of linear momentum. If the X-ray source, if the X-ray radiation, the electron are behaving like point particles that undergo collision, we must have conservation of linear momentum and conservation of energy. And this problem is a little bit more complicated because it's a two-dimensional collision. It's a two-dimensional collision, okay? So let's start with our equations. It's a little bit lengthy, but it's worth it, the derivation, okay? Looking at the experiment performed by Compton and Debye, we can come up with the following equations. Okay. Initial energy, right? Initial energy of my photon plus the rest energy of my electron. That's the net energy of the system. Conservation of energy equation, right? Conservation of energy equation. Net energy at time t equal to 0 must be equal to the net energy of the scattered photon plus the kinetic energy of the ejected electron plus its rest energy, rest mass energy. Here's an equation of conservation of energy. We can even simplify that because those two terms cancel out, right? The next step is to get the conservation of linear momentum. That's the initial linear momentum of the X-ray photon. That's the final linear momentum of the X-ray photon. And that's the final linear momentum of the electron, right? So here you go. Conservation of linear momentum. Initial linear momentum is equal to the final linear momentum times the angle cosine of theta. Okay, but that's just part of the equation, right? Now we have to consider the linear momentum of the electron as well. The linear momentum of the electron, I'm going to call it P cosine of phi, like that. That's just the x component, conservation of linear momentum. X component. Y component. Y component is going to be, well, here, initial linear momentum in the y direction is going to be 0, right? The linear momentum of your photon, it has no linear momentum along this direction. But the scattered photon and the ejected electron, they do have a linear momentum in the y direction. So we're going to write like that. The linear momentum of the photon, here you go. This P1 here is equal to this P1, it's the same, right? And then we are going to have a similar equation, but it's going to be sine of phi, and we must have a negative sign because the electron is moving in one direction and the photon is moving in the other direction. We know E naught, right? We know this term here. But we do not know, we know P naught because we know the frequency, but we do not know those terms here, P1 and P. Okay, but hey, there's something missing here. Hey, there is something missing here. Nobody told me that, right? Something missing here. Recall from the photoelectric effect. Recall from the photoelectric effect that we still must provide an energy to the photon, to the photoelectron, right? To the photoelectron to be ejected from the nucleus, from the plate. An energy that we call the work function of the metal. I didn't include that there. Did you notice that? I did not include it there. Did you notice that? Okay, and there is a very good reason why I didn't include that. And there is a very good reason why I did not include it. Okay, recall that the work function of metals is anywhere between 2 and 6 electron volts. Okay, recall that. That corresponds to the UV range. That corresponds to a photon in the UV region of the electromagnetic spectrum. Okay. Now, what if we are using not a UV photon, but an X-ray photon instead? How does its energy compares to the work function of the metal? That's the question that you have to ask yourself, okay? Well, the answer here is very simple. The answer here is very simple. Because we're dealing with UV, with X-ray energy, the energy of the photon is much greater than the work function of metals. Because it's much greater than the work function of the metals, okay? We can neglect it in our equation. And that will simplify a lot our work, okay? That would simplify a lot our work. And you can even do some mathematical calculations, right? Let's do some mathematical calculations. Let us do some mathematical calculations. Of the initial energy of the photon. So you can feel confident that this approximation is reasonable, right? Let's do that. Let's take a look at the frequency of UV light. UV, not UV, the X-ray, right? UV, X-ray wavelengths region. Wavelengths region. They have wavelengths ranging from 0.01 to 10 nanometers. frequency on the order of 3 times 10 to 19 and 3 times to 16 hertz. Okay, that's the range. 3 times 19 correspond to the shorter wavelengths. 10 nanometers correspond to the lower frequency. There is an inverse relation, right? So let's get our spreadsheet here. Let's see if it makes sense. This approximation that I'm mentioning. Okay, X-ray, frequency of X-ray. There is the lower end, the lower bound, and the upper bound, X-ray. Frequency 3 times 10 to the 16. 3 times 10 to the 16 hertz. And the other is where did I get it? Now I'm lost. What happened here? Here? No, not here. Must be here, right? No, that's green light. That's not UV light. Oh, I'm lost here. Yeah, what's happening to my UV page, right? Okay, looks like I gotta do that again, all over again. Okay, so let's do that again. X-ray frequency range. Let's look at the numbers. Exahertz. See, this guy here is the power, okay? 10 to the 16, 10 to 16 to 10 to 19, right? 10 to 16 to 10 to 19. That's the frequency. And let's see the ranges. Three orders of magnitude. Here we're just proving, we're just checking whether that approximation is correct or not, right? So we're going to know, we're going to figure out whether the energy HF, but you gotta get that in electron volts, okay? And we got the H in electron volts here. We need the H here. Okay, electron volt seconds. All I have to do is to multiply this term by this term. And I need to put a $sign here. Okay, and look at the values of the energy in the lower part of the X-ray. The lowest value of energy of an X-ray photon. Okay, it goes from 124 electron volts to 124 to, let's see, I want to put that in numbers, right? So you can see this guy in a better light. Here you go. 124 to 124,000. So compare that to 2 electron volts. Compare that to 6 electron volts. 6 electron volts, which is the highest, value of the work function, is much less indeed than the lowest possible value of the energy of your X-ray photon. We can even come up with a, percentage, right? What's the percentage? Did you get the idea? It's so small. It's almost 1%. It's a little bit more than 1%, right? Maybe 2%. Let's see how much percent. I'm going to put it 100 here. 4%. Less than 5%. 4.8% is negligible. And then if you do for the other, it's going to be even lower. It's 1,000 times less. 0.004%. Did you get the idea? We can indeed neglect the work function of the metal compared to the energy of your X-ray photon. If we, adopt that simplification, if we adopt that approximation, we're going to incur in an error that's less than 5%. Okay, so that's what I did, and there's one more step here. So that's the reason we are, we excluded the workforce. We excluded the work function of the electron because its value is less than 5% of the energy of the X-ray photon. Okay? And what do you want to do? Okay, we want to get a relation in terms of the initial and final wavelengths. Okay, wavelengths in terms of the angle theta. That's what we want to do, and compare to Debye's and Compton's experimental result. Okay, so let's go back here to our. Here you go. What you see right in here is a detector. This detector can be an X-ray spectrometer that uses a grating as well. Remember that chapter that we didn't cover about X-ray diffraction? That's the type of device that we use to measure the wavelength and consequently the frequency of the X-ray. And remember that we are not just emitting a single photon here, we're emitting a stream of photons that come towards this metallic plate. Okay, I'm going to show you the experimental results first that Debye and Compton obtained, so you can understand what's going on here in experimental sense. Okay, right in here, photoelectric effect. Here you go, a similar setup, right? The experimental setup that I described. Mine was simpler. It's easier to understand my setup for the photoelectric effect. And work function, photons, momentum, Compton scattering, light interference. Okay, we have here a similar drawing. The only difference here is that's the target or the metal plate. What you see here are collimating slits. You want to make sure that the X-ray is not irradiated in every possible direction, but just in a straight line. What you see here is just a slit, let's say a lead slit, right? That will ensure that only X-ray in the straight direction hits the target. And then you have your detector. You have your detector, okay? Oh, whoa, Jesus Christ, I didn't do it right. Here you go. Let's go back here. Good. Oh, and here are the experimental results by Compton and Debye. Okay. What we have here is the intensity of the X-ray light, okay, against the wavelengths. Against the wavelengths. Phi, let's see what phi is. Phi is what I call theta, okay? In my experiment, I call this angle here theta, and the other I call phi. If this angle is 0 degrees, if the detector is right in here at this spot, okay, we do observe a peak around these wavelengths. It looks like 71 picometers. Okay. There you go. I'm back here. If we put our detector at an angle of 45 degrees, then you're going to start seeing two peaks. This main peak here that was around 70 something picometers, which by the way is the original wavelengths of the X-ray. Okay. See, although there is only a single wavelength in the incident X-ray beam, right? In the X-ray beam, so that should be 71.1, okay? Compton apparatus, a beam of X-ray of wavelength 71.1 is directed on the carbon target. They put a carbon here. The X-rays is scattered from the target are observed at various angles. So as I change the angle phi, I start to see that in addition to the original wavelengths, I'm going to have another wavelength that's being scattered, that's being created, a different wavelength value. There's a delta lambda shift here. The higher the angle, the higher the difference, the higher the wavelength shift. Okay, so what's happening here? What's happening here, this beam of X-rays is incident in the target or in the metal, and it's being scattered all over the place. Okay, the initial X-ray beam moves straight, but when it interacts with this target, it gets scattered all over at several different angles. And the further away you are from the main direction of the beam, you start to see wavelengths that are different from the original wavelengths. Okay? These wavelengths here, by the way, is less energetic than these wavelengths here. These wavelengths here has more energy than these wavelengths because it has a longer wavelengths. Okay? And as we move further and further away, here you go. The delta lambda keep on increasing. See that at 135 degrees. That was the experiment. That's real data, real life data that he got. Think about the light, right? Light behaves in this way too. It can be scattered, and so X-ray can be scattered as well. Here is just a wavelength of the X-ray. So let's see if this theory that we have matches or not the experimental result. That's the idea that they propose, and they use Einstein's results of special relativity plus Einstein's proposal that the energy of the photon was hf. Okay, and let's continue here with our equations. I'm going to remember those are the equations that we started. It's very lengthy, this derivation. Okay, watch out for that, but it's worth it doing. Okay, recall I have three equations. Okay. Have three equations. I'm going to highlight what I know and what I do not know. We do not know P. We do not know P1. Okay. See here, three equations. And recall that the initial and final wavelengths in terms of the angle theta, because that's what the experimental result is providing us, right? We want to get the following. We want to get lambda equal to a function of theta. Symbol. Here's a function of theta. I'm going to put this guy as a symbol. Okay. But it's not just one wavelength, it's gonna be the second wavelength as well, lambda 1 as well. And in order to do that, we have to eliminate a bunch of things here. We have to eliminate a bunch of things. Lambda and lambda 1, just not lambda, to get lambda and lambda 1. That's a function of theta. Because the data, because this theoretical result must be compared to this real life data that you have here, okay? I want to keep theta, but I want to eliminate phi. I want to eliminate phi. What else do I want to eliminate? I want to eliminate U1, right? I want to eliminate the kinetic energy. How are you going to do that? Right? And I'm going to, here you go, I'm going to simplify this equation, right? I didn't do that before. Let's do that now. I want to eliminate E0 as well. And I want to come to a final equation. Oh, and by the way, that has only lambdas in there as a function of theta. How do we do that? We want to eliminate the following. We want to, now you're going to understand why this problem is so difficult to solve mathematically, okay? We want to eliminate the following. We want to eliminate E0, E1, the kinetic energy, P0, P1, and phi. That's what we want to eliminate. And at the end, I want only lambda 1 and lambda as a function of theta. That's all. Phi. Let me put F here, and so I can put symbol. Here you go. Phi. I'm going to italicize 1, 2, 3, 4, 5, 6. I want to eliminate 6 parameters. And we have only 3 equations. We have only 3 equations to that. By eliminating, I mean, we have to write all those 1, 2, 3, 4, 5, 6 parameters in terms of known values, in terms of lambda, in terms of lambda 1, okay? The first step is the following. I didn't use all my equations yet. There's some other equations here that I didn't spell out. But the first thing that you're going to do, you're going to use is Einstein's relation for the energy of the photon. That's the first one. And then we must relate the frequency of the photon with its wavelengths, right? Remember, I want my lambda and lambda 1 at the end of the equation. So that's how we start. And then we can do the same for E1, for the energy of the scattered photon. Go, and here you go, my lambda 1 here. We know H, we know C. And we want to find out what's going to be lambda 1 minus lambda. That's what we want to do at the end. Okay? So why do I want to know lambda 1 minus lambda? Lambda 1 minus lambda is exactly this distance here, is my delta lambda. My experimental results is providing this data. Okay? And what the book called phi, I call theta. Okay? So little by little, we start to eliminate those, those parameters that are not, that we don't want to keep. That one, here you go. I eliminate E naught. I eliminate E1. Okay, so I don't need that anymore, right? Since I eliminate them, maybe I'll get back to them later on. And now I have to think how I'm going to write down my P naught. Remember the P naught? There is a relation between P naught and the energy, right? One more equation. One more equation here. And by the same token, we have a relation between P naught and the energy. We also have a relation between P1 and the energy. Remember, P naught is the initial momentum of the photon. P1 is the final momentum of the photon, the magnitude of the final momentum of the photon, right? So that's going to be E naught divided by C. This relation comes from relativity. Here we have FHF, right? And one more step. Here we get C divided by lambda. Okay, like that. And then finally, what we end up getting, C cancel out with C. That's what we get. If we follow the same procedure, we will get a similar result for lambda. So that's how the momentum of the photon can be written in terms of its wavelengths. Okay, so let's use those two momenta. Well, I don't want to overwhelm you. That's why I'm getting, eliminating some of the parameters that we used. Let's save it before it crashes, right? I'm going to substitute P naught right in here and P1 right in here. P naught goes here. P1 goes here. Here and here. Like I said, it's not easy to do this derivation. Why is not easy to do this derivation? I'm going to write that down here at the top. It's not easy to do this derivation. It's not easy to do this derivation because we have multiple equations. Not just three, we have more than three. So far I'm using 1, 2, 3, 4, 5, 6, 7. So far I already used 7 equations. We have a system of multiple equations. More specifically stating, more than 3 equations that we must handle to come up with a final result. That's how difficult this problem is. But if you follow those step by step, those steps that I'm providing to you, you'll be okay. Okay? So here you go. Now I eliminated everything. Here you go. I eliminate everything that I had to eliminate. Look what happened now. So far I used 7 equations. Those 3 initial equations for conservation of momentum and conservation of energy. But then I used these other 2, 3 plus 2, 5, 3 plus 5 plus 2, 7. I used, until this point, 7 different equations. And I told you that I want to get a relation between lambda 1 and lambda 2 in terms of the angle of observation theta. So I must somehow eliminate the remaining parameters: kinetic energy, linear momentum, and phi, and the angle phi. Do you see now that we have 3 equations for 3 unknowns, or 3 parameters that we want to eliminate? Now we can do that. When the number of equations is equal to the number of unknowns, then you have a much better chance of solving your problem. okay? And the way we are going to do is going to be the following. Okay, let's go back here. 1, 2, 3, 4, 5, 6. From our 6, I'm not going to say unknown, I'm going to say undesirable, right? Undesirable parameters. Now we are left with only 3 and 3 corresponding equations. So what's the next step? Remember, I told you that I want to get lambda and lambda 1 as a function of the angle theta. That's the goal here. So we can compare my theory with the experimental results. We somehow must, get rid of this P, phi, and kinetic energy. Okay, the first step, is the following. I'm going to do a Caesar, okay? What is easier now is to make this one here equal to this one. We have a 0 on the other side, right? The negative sign when passed to the other side becomes positive, and that's easy enough. And then I'm going to do the following. I'm going to pass this term to the left. When we pass to the left, we isolate those parameters, those undesirable parameters, right, from the desirable parameters. What is the next step? There are different ways of dealing with this problem, okay? Deriving this problem. What I'm providing to you is one that I have here in my notes. The next step that we're going to do. Okay, I'm going to copy this step downwards below, okay? And what I'm going to do next, let's recognize that there is a P cosine of phi and there is a P sine of phi. If we want, we can eliminate the P's and get a tangent of phi in terms of our parameters that we want. But I'm not going to do that. I'm going to do something different. I'm not going to eliminate the P. I'm going to eliminate the angle phi. And I'm going to eliminate the angle phi by squaring the left and the right side of these equations. Okay. Remember think about Debye and Compton doing this derivation for the first time in their lives. Today we just teach students how to do that because we know all the steps, what it takes to get what we want. But Debye was doing that and they were not sure. Debye and Compton were doing that and they were not sure if those formulas would work or not because those were brand new theories. Think about their mindset when they're trying to derive those things. Is it going to work or is it not going to work? Am I doing the right assumptions here? Right? That's what they were thinking. And then now that I achieved something like that, I will be able to eliminate this cosine and the sine of phi, the phi angle. I'm going to combine those two equations into a single one. And let's see what happens. Right? Sum this one with this one. And then voila, right? We didn't finish yet, but we're almost there. Remember, we have 7 equations, now we have only 2. How lucky you are, right? How lucky we are all. See, this term here is going to be like that. I still have this term here that I must expand and figure out whether we can simplify or not. If you look closely, this term is going to result in 3 terms and this one in a single term, a total of 4. But wait a minute, When I square this term here, I can combine it with this other term here. So out of 4 terms, I'm going to eliminate 1 because we're going to have cosine square and sine of square, right? That's what we are going to do. Do you see that coming? Do you see that coming? Right? But let's do something else before we get into that. There is one more equation that we must use because there must be a relation between the kinetic energy and the linear momentum. And the linear momentum here, that the linear momentum of whom? Let's go back to our drawings. The linear momentum of the electron. There must be a relation between them. The particle that has mass. And in order to find that out, we are going to use that other equation of Einstein for special relativity. Where is it? Where is it? Where is it? Here, right in here. The equation of special relativity, and that's the energy. This time is going to be the energy of the electron. Okay? Let's emphasize that this term here is the energy of the electron. Here's the mass of the electron. Here's the momentum of the electron. So why am I doing that? Because I need to relate the kinetic energy with the linear momentum that was left here in this equation. And I'm going to do a next step here. So we have something like that. And what I'm going to do is this energy. I'm going to rewrite it in terms of kinetic energy and rest mass of the electron. That's what we are going to do here. Like that. Now, do you see the kinetic energy here? Do you see the P here of the electron? Do you see that the rest energy square of the electron is going to cancel out as the rest energy square of the electron? Right? So let's go another step. I'm going to do this calculation separately. I don't need that anymore, right? I will square this term. I will square this term. It's going to become force power of this term. 2 KE not C square. Like that. Like that. We'll separate that. We're going to come back to that. We are going to get a relation for the kinetic energy in terms of the P. Or the P in terms of the kinetic energy. Either way works. Right? Either way works for me. M naught square C to the force power cancels out. Okay. We are better off because we have kinetic energy at 2 places here. We don't want to solve for the kinetic energy because it's going to be that mass of square roots, right? We are better off solving for the P. That's why we're better off. And P squared, by the way. That's the point where we have to make decisions in your equations and figure out what's the best course of action, right? And we find that P squared, we find the best course of action is to solve for P squared. With the kinetic energy divided by C squared. The C squared canceling out. Okay. And P squared here, I will write that down. Okay. Let's put all the three equations together to see how challenging it is to do this derivation. And in the past, right, I believe I put the negative sign here. So you can write down the kinetic energy in terms of those two. I'm going to separate those here. Okay. And let's see what's going to happen. I'm going to put the kinetic energy here. So we're going to use this equation right in here. Okay. Actually, we're going to do this one here, this one right here, the unknown parameter P. Okay, that's what we want. We want to get this one right in here. Just like I said, eliminate P first, right? Because it's easier to handle this way. Okay. So eliminate P. Eliminate P. And now I don't need that P square, right? Eliminate P square. We have to say P square. Okay. And then what's going to be the next step? The next step is we're going to get rid of the kinetic energy term. Now eliminate kinetic energy. I'm going to just copy this guy and plug it in here, and then the this way. Now we achieved our goal. We got lambda and lambda 1 as a function of theta and other constants that we already know, the rest mass of the electron, the velocity of the light, the Planck's constant. But we managed to do that. Right now, the question is just to do some hard work here to put this equation in a better format. In a better format. Let's put it in a better format. Lambda square, lambda 1 square, h square, cosine square. And the cosine square must be a positive number. And I'm going to emphasize. Let's see, I'm gonna copy this one here, right? I'm gonna put the cross term as the last term because it's more convenient for me to do that. I must expand this one as well, right? Square, lambda square, 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 and then we need the cross term again. Oh, don't forget this one is going to be a positive, right? Cross term is a negative sign. Two. Right, yeah. And I gotta get rid of this negative sign, and I have to get rid of this square term. Gotta be very careful when we do this derivation so you don't make a mistake. If you have long derivations like that, you're bound to make mistakes. Okay, that's why it's so important for us to use computers. Computers, they save you on the amount of time and amount of proper derivation. Now I'm going to cancel those c squared here. We have a c squared here as well. And when okay, like that, the c squared disappeared. The c squared downstairs disappeared. And let's see if we can do any simplification. The problem is almost done. It's just a matter of putting it in a more intuitive format. The derivation is done. It's just a matter of putting that in a more intuitive format. See here, this guy here, cancel out this one. I'm going to emphasize that they cancel out. Because they cancel out, we can remove them. Okay, this term here combined with this term here, right? So let's go ahead and combine them. Right here. I'm just commuting the terms, right? Can we do something else? Let's see if we can do anything else here. We have cross terms here. Oh, what about this one? No, we cannot do anything about that. Yeah, it's okay. So let's do what's easier. And then after doing what's easier, we figure out whether we can do better. Better than easier, right? Oh man, look there. Look at this term. What a beauty. What a beauty. Isn't that? I'm gonna highlight that. That big mass is becoming more and more intuitive to understand. I'm going to do something else that I didn't do yet. I'm going to factor. I should have factored that before, right? But let's factor that now. Let's factor that now. It's going to be 1 here and 1 here. The 2 cancels out. The h is going to be squared. Okay. Oh, I did that in the wrong place, right? Let's see what I did here. Yeah, I did that in the wrong place. Here, I'm supposed to do it here. Here you go. The lambda 1. What else can we do it? Okay, we can cancel the h's. That's the next thing we can do. H, and H. Okay. Oh, the 2, and and 2. Okay, the C is in there. M naught is in there. What else can we do it? Okay. Oh, there is one more. There is one more little hidden simplification. Notice that we have lambda, lambda 1 here, lambda, lambda 1 here. And what about here? Can you put a lambda, lambda 1 there too, downstairs? If we do that, we can cancel, right? Keep it the same. The same denominator. Lambda and keep the same denominator, and we are about to solve this problem. I don't need this term here. Okay, note, see that we have lambda, lambda 1 here, lambda, lambda 1 here. I'm going to put this M naught together with C to simplify the format of my equation, right? One more. What time is that? 10:15, 10:35. Wow. Time for the break, right? Lambda, lambda 1 disappear, right? And now we gotta put my parentheses back here. And look, folks, are you seeing delta lambda here? Do you see the delta lambda coming here? The difference? Okay. Going for another one. Plus H. Plus H. Okay. The plus H, we can collect. Okay. And almost done, right? Oh, I'm gonna do something else. I'm gonna here write this term here as lambda H. Remember, every time, most of the time when we have scattering, the final wavelengths is more than the initial wavelengths. It's just a question of conservation of energy, okay? So here we go, almost done. What I need is just this term here and the other one. The C goes downstairs. Okay, Cm naught goes downstairs. Delta lambda is written down like that. And by the way, this term that you see here has the same units as this term. Whether it's nanometers, whether it's meter, whether it's picometer, because this term here has no units whatsoever, right? So because this term has units of wavelengths, we give it a name to this term. We call it, just to simplify the equation, we call it the Compton wavelengths. Okay? We call it the Compton wavelengths, and finally, my delta lambda is equal to that. And this relation, let's see here, what happens at theta equal to 0, right? I'm gonna do just one here, theta equal to 0. See that? a theta different of 0, we have two peaks that can be clearly seen. At theta equal to 90 degrees, we have again two peaks. At 135, we have two peaks again that we can clearly see. But what about a theta equal to 0 degrees? What happens to the delta lambda, right? At theta equal to 0 degrees, cosine of 0 is 1, and the difference in the wavelength between the two peaks is 0. They merge into one another. Exactly what the experiment shows. Let's see if we can do better than that. Let's see, we have 45 degrees. Let's do 90 degrees at easiest, right? Let's do 90 degrees at easiest. What if theta is equal to 90 degrees? 90 degrees. Okay, here becomes 0. Okay, 90 degrees cosine of theta becomes 0. And the difference in the wavelengths is equal to the Compton wavelengths. Okay, you can plug in the numbers here, right? And see if matches what you see here or not. Apparently the difference is around what 72.5 here, 75, looks like 73 here. Looks like we have 2 picometers. Try to do that at home and see if it makes sense or not. So that's the Compton scattering experiment, a historical experiment that we introduced to you all because this is a very successful theory and also kind of a simple theory. Simple in terms of derivation, physical understanding of the equation, but not in mathematical terms, right? Mathematical terms is lots of work to derive a final equation that matches the experimental results. Okay, so this in conclusion, the Compton scattering lent support to Einstein's theory of the photon. Okay. And the relation between its energy and frequency. That's the conclusion here that we get. Okay. So when you go home, try to match that equation to what you see here, so you can have a better understanding what's going on. Okay, so let's review this Compton experiment. Let's review this Compton. Note see that the peak wavelength of the original X-ray appears everywhere. Did you notice that? It doesn't matter what the angle is. We have the original wavelengths of the X-ray at 0 degrees. We have the original wavelengths of the X-ray at 45 degrees. We have the original wavelengths of the X-ray at 90 degrees and 135. Okay. And what is surprising here? What is surprising here? That we have the second peak here, this scattering term of the X-ray. Scattering term here, another scattering term here, and here. All of that explained in terms of the equations of Einstein. Okay, what else do we have here? For the quantitative part, we first apply the law of compensation, so just collision between and as a result of the collision, X-ray of wavelength lambda prime moves off at an angle phi, and an electron moves off at an angle theta as shown. Conservation of energy give us in which HF is the energy of incident X-ray photon, HF prime is the energy of scattered X-ray photon, K is the kinetic energy of the recoiling electron. Because the electron may recoil with a speed comparable to that of the light, we must use the relativistic expression, but we didn't do that, right? We didn't do that, but we didn't have to do that. Okay. So here you go. Here's another way of looking at the X-ray, the collision, right? One more minute before 10:45. Let's take a quick look here. The X-ray approaching the electron. Remember, this is the plate, right? This is the metal plate with electrons in there. The X-ray can bypass the electron scatter angle of 0 degrees. No energy is transferred to the electron. Or two different ways. Or it can scatter at some intermediate angle, phi. Intermediate energy is transferred. Okay? Or it can backscatter. There is also this possibility. You know, angle theta equal to 180 degrees. We can have that too. Angle theta equal to 180 degrees. The electron moves forward, the X-ray moves backwards. Okay, so 10:45 right now. Let's have our break. Any questions? Break from 10:45 a.m. to 11 a.m. Okay, I will save this thing and let's go for our break. Oh, let's see. Sartak, okay. No, okay, no messages here I haven't seen yet. Okay, so see you in 15 minutes. Okay, so we're back here. Let's take a look here at our book, right? Okay, here we have the relativistic correction for that, which we're not doing, okay? So that's what your book is doing right in here. He's already going to light as a probability wave. We are going to talk about that, but let's start from the very beginning of this chapter to make sure we are not missing anything else, right? 38 photons and matter. Okay. Quantum of light, photon, the quantum of light. So you must have the best way of understanding what a quantum of light is to think of the photon as a particle. Okay, a particle that, but it's not just a particle, it's more than that. It's a particle wave, it's a mixture of particle and wave. That's what the photon is all about. Under certain conditions, it behaves as a wave, like in the double slit experiment, Young's double slit experiment. And under other circumstances, it behaves as a particle. And the best way of describing the photon is in terms of the beating effect that we have seen before. When we have two waves combining with each other, the wave becomes kind of concentrated in a single spot. Do you remember that? It was like a lobe, a big lobe that would repeat itself. But that's what happens when we combine only two different wavelengths of the wave. If you combine 3, 4, 5, 6, 7, 100 wavelengths that is slightly off by frequency, that big lobe that you see in the beating effect becomes narrower and narrower. That's what they call quantum of light. Is a wave that becomes more and more localized to a point that starts to behave like a particle. That's what the quantum of light is all about. Okay, so let us write it down here. I'm going to summarize what we have so far. Summarize what we have so far. And you are going to see very soon, you're going to see this quantum of a wave that I'm describing. Okay? Okay, here you go. I'm going to describe that to you right now. Summarize what we have so far. One. We saw, in geometrical optics, that light and electromagnetic radiation in general behaves as a light ray that travels in straight lines, just like a particle does. Then, we learned that under certain conditions, light exhibits an interference pattern reflecting the fact that it also behaves as a wave. Finally, in the 20th century, we came to the realization that light behaves both as a wave and as a particle. Just recall, right? Just recall the double slit experiment. What we call, and by the way, what we call a quantum of light, which, by the way, is best described in terms of the beating effect. Okay, I'm gonna give you an idea what the beating effect is all about. You already have an idea, right, what the beating effect is all about. I have here an illustration of a wave, right, of a monochromatic wave of a given frequency, of a sharp frequency. It behaves just like a sine wave, described just like a sine wave. But remember, when we combine two waves of two different wavelengths, two different frequencies that were doesn't have to be close to one another, two different frequencies, point, period, right? What started happening here? What started happening that whereas the wave was spread out throughout the whole space, when we combine two wavelengths, now the waves start to be concentrated on a specific regions. This concentration is illustrated by the amplitude of the wave. That's the beating effect that we experienced that when I combined two sound sources of different frequencies. I did that in the classroom, remember? So that's something like that that you see. You know, the wave that was initially spread out evenly throughout the whole space, and spread out throughout the whole evenly throughout the whole space means their amplitude was spread out evenly throughout the whole space. Now it starts to become concentrated on some specific regions, producing this type of lobe pattern. You can do that, by the way, okay? When you sum two waves of slightly different wavelengths, in this case, the delta K is related to the wavelengths, right? Delta K is K1 minus K2. K is 2 pi over lambda. 2 pi over lambda 1 minus 2 pi over lambda 2. When this difference is 0.04 divided by m, you get this pattern. Then, as you sum more and more waves, here's the summation, right? Two sine waves, that's what this thing generates. You can do this experiment yourself. K1 equals to 2 pi over meter, and then K2 is 2 pi meter plus 0.04 over meter. That's the unit of the parameter K. If we keep increasing the number of sine waves in the sum, okay, something interesting, very interesting happens. Very few books discuss that, okay? Books, they stop writing here. But if you keep on increasing the number, and then here's for 3 different sine functions, okay? You get a concentration in this lobe, right? That repeats itself, and then you start to see another little lobe nearby, okay? As we increase even more, okay? N equal to 3 here, see that? N equal to 3, 1 small lobe between the large lobes. What about N equal to 5? 3 small lobes between the larger lobes, right? 3 stands for 1 smaller lobe. 5 stands for 3 smaller lobes. So 4 should stand for 2 smaller lobes. It has some mathematical properties, right? If you keep on adding those things, and in this case, you're going to have 100 N equal to 100 sine waves summing each other with the same amplitude. Look what starts to happen. We start to have a higher and higher concentration of the waves in a given point. This is a typical behavior of point particles. A point particle is restricted to a single spot in space, and that's what's happening to those waves. They are starting to become restricted to a single spot in the space. And look also the separation of those lobes. It's something around 160, right? What about here? Oh, we cannot see, unfortunately. Okay, we cannot see the numbers, unfortunately. But the distance here is less than the other one, I can tell you for a fact. Okay, I did this simulation over and over again. Okay. So we have this interesting behavior of these waves. Okay. Here, another one. This one is how many? Oh, this is 100. Okay. 0.08. And now what am I going to do? Look at the separation. Here is 160, more or less, right? 160 units from one to the other. And here, what we're going to do now, we're going to do the following. First, okay, we started to sum the sine waves with the K factors, having a delta K equal to 0.04, okay? From each consecutive wave, okay? K1 minus K2 is 0.04, K2 minus K3 is 0.04, and so on, okay? Now, what happens if this K1 is not 0.04, but the delta K is not 0.04, but the delta K becomes larger. Okay, I still have 100 sine waves, but now I'm gonna change the delta K. Look what happens between the distances of the lobes, right? For 0.04, the distance between the lobes were approximately 160. But for a larger distance between delta Ks, the distance between lobes is less, something around 90. Okay. And here's 0.12. They get even closer. Now it's 50. You see that? Let me summarize what we're doing here. So what you're seeing right here, folks, what you're seeing right here is what we call the packet of waves. One packet of wave here, another packet of wave here, another packet of wave here. That's what they call packet of waves. In reality, when I was performing experiments with gamma rays, I went to that place there, or that guy that has this corporation in Canoga Park. Okay, he put his detector in his gamma ray detector. I was using my own optical fiber, my own technology, combined with his own technology. Okay, and he was using his detector. What did we sense? What did the detector did? The detector has had a sound. Okay, it was just saying tick, 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 just like Geiger counters that we hear in the movies, right? So what was happening here? We have this gamma ray, which is an electromagnetic radiation that's not coming out together into the detector, but little by little, you have these little packets of gamma rays that incident the detector and causing that sound, tick, tick, tick. So that's what I heard at that moment when I was doing the experiment with this guy. You know, gamma rays, be careful. You cannot handle gamma rays easily. When I was there, that guy has already been doing those experiments for a long time. He didn't care about the gamma rays, but he came to me and said, you know, look, Claudio, now I'm going to expose the source of gamma rays that, by the way, is shielded by this LED. I want you to go to the other side of the room so I can uncover the gamma ray source. And I do not know why the guy was brave enough to be exposed to those gamma rays, but he was doing that exactly. He had this rod with a gamma ray source here at the tip, right? That rod was surrounded by LED, while the LED was surrounded the gamma ray source. The detector was not detecting anything. But the moment that they raised that rod with the gamma ray source there, the detector started to doing that little noise, tick, tick, tick. The packets of gamma rays incident in the detector. Okay, light behaves in this way as well, visible light, but the packets are not as much compact as the packets of gamma ray and X-ray. Okay, I'm going to talk more about that. Okay, this is more the rest of this discussion is more appropriate for particle waves, but it's important that you have this picture for electromagnetic waves as well. Let's see. I think so. I think so, Raymond. You know, Raymond is asking if you do a lot of physicists with that gamma rays tends to get cancer. Yeah, I believe so. I haven't looked at the confirmation of this feeling of mine, this gut feeling of mine. But if you go back to those guys who built the atomic bomb, for instance, okay? Oppenheimer, Feynman, and many others. Oppenheimer died of cancer. Richard Feynman died of cancer as well. Is it coincidence? They were working with nuclear physics, right? They were working with atomic weapons that emanate gamma rays, that emanate X-rays. Okay, so I suspect that yes. I do not know about this other guy that I was working there in Canoga Park. I never managed to contact him again. But I was a little bit concerned that he was brave enough to raise his gamma ray source and stay like there right in front of this rod with the gamma ray source at the tip of it. I was really concerned. And then he gave me this little sample with some particles that was emitting beta rays. Okay, beta rays, alpha, beta, and gamma, right? There are three types of nuclear radiation, alpha, beta, and gamma. Gamma is the electromagnetic radiation. Alpha and beta are particle radiations. They are not electromagnetic waves, but they are particle radiation. One is the electron in the nucleus, the electron surrounding the nucleus, and the other one is a combination of the nucleus itself. That's something that we study further down. But that guy gave me that little sum of beta. I shouldn't have taken that with me, because even today I keep on thinking, is this guy serious about that? Give me a sample of water that has particles that are emitting beta rays, nuclear radiation. He told me it was okay. I didn't have to worry about that. He told me I should worry about alpha rays and gamma rays, but not beta radiation. Okay, so let me document what I wrote here for you, right? We saw in geometrical optics that light and electromagnetic radiation in general behaves as a light ray that travels in a straight line, just like particles do, right? Particles do. Just like particles do. Then we learned that under certain conditions, light exhibits an interference pattern reflecting the fact that it also behaves as a wave. Just recall the double slit experiment. Finally, in the 20th century, came to the realization that light behaves both as a wave and as a particle, what we call a quantum of light, which is best described in terms of the beating effect that we saw for waves, specifically the beating effect of sound. But this beating effect can also be extended to light rays as well, to other types of waves. So when we talk about a quantum of light, we are actually talking about an electromagnetic wave that has this beating effect, right? And I should write that down here. Recall that in a beating effect, the wave becomes more and more localized. Whether it is two waves of different wavelengths, 3, 4, or 100, okay? Or 100. And I want you to remember those graphs that I displayed for you. This is what we call the quantum. The quantum of light. The quantum of light. Okay, so I'm going to just review what I said about the summarizing, right? What you saw about the beating effect. 1, when you have a single monochromatic sinusoidal wave, when you have a single, monochromatic, sinusoidal wave, the wave is described as being everywhere in space with the same amplitude, right? However, when you add a second wave to the first one of different wavelengths and frequency, comma, you start to, you see, there you go, you see a lobe, right? Concentrated in a given region and evenly spaced, right? That's what you saw there. Is the description, what I mentioned to you. Here you go. Here's the lobe, only 2 sine waves, one lobe here, another lobe here, another lobe here, evenly repeating itself. Okay? If you add a third wave, you still see a large, you still see a larger lobe, right? But this time with another one surrounding, you still see larger lobes, not just a larger lobe, but larger lobes, but this time surrounded by a smaller one. Okay, so 3 waves, one smaller lobe in between the larger ones, right? You add a fourth wave. This time you see a larger lobe. You see larger lobes surrounded by 2 smaller ones, right? 4 waves, 2 smaller lobes in between the larger one. See? 3, 1, 4, 2, 5, 3, 6. Did you get the idea? Okay, 6, 4. So we have this interesting mathematical relation for the number of sine waves and the smaller lobes. Okay? And sine waves, when summed up, generate n minus 2 smaller lobes in between the larger ones. Can you remember that? Finally, when you have 100 sine waves, the smaller lobes becomes so small that we can hardly see them, but only the larger lobes spaced by a given distance and very localized. Okay, and very localized. So remember that here, 2 sine waves, 3 sine waves, 5 sine waves, 100 sine waves. Look at their localization. We have smaller lobes here, but they're so small that we cannot see them. And look at the localization of the larger lobes. It has a very high amplitude here, right? That decreases very quickly. By the way, this is the characteristic of a point particle. A point particle has this extension that is very small, right? Localized in the space. Keep that in mind. And now we can start covering something else. That's what I want to share with you. Okay, we're going to go back to this model of the lobes. Okay, and now we have that waves have particle behavior. Light has energy and momentum, and it undergoes collisions with material particles, such as electrons. Okay, such as electrons. It is at this point that sometimes someone start asking the question: if a wave behaves like a particle, is it possible that particles also have a wave behavior? You know, that's the complementary principle. We call that the complementary principle. If one thing happens in one way, that's the other thing happens in the other way. That we call it the complementary principle. That sometimes is not obvious. It's not that obvious. Keep that in mind. Okay, so if certain waves behave like particles, is it possible that certain particles behave like waves? Okay, that's where we get to the point of the wave properties of particles. Okay. And let's go back to our equations again. Energy is equal, right? Energy of a photon is equal to HF. Can you remember that? And which, by the way, is Hc over lambda. But we also have that relativity result, that result of special relativity. E squared, net energy squared, is equal to momentum squared times the speed of the light squared plus m naught squared times c to the fourth power. Okay. Now a photon of zero mass, you already know, right? You already know that a photon of zero mass, for a photon of zero mass, there is this relationship between energy and momentum. E equal to Pc and P, for the photon is still for the photon. E is equal to HF or C over lambda. Okay, the C's cancel out, and we get this neat relation that the linear momentum of the photon is related to its wavelength. It's related to the wavelength. And then in 1923, someone called Louis de Broglie was doing his PhD thesis, right? And he starts thinking, you know, just like I said, he starts thinking in the terms that in terms of the complementary principle. If light behaves as a particle, is it possible that particles behave like a wave, right? If waves has this particle behavior, right? Light that is a wave has this particle, this corpuscular behavior. Is it possible that particles such as electrons, protons, neutrons, is it possible that those particles behave like a wave as well? There's an example of the complementary principle at work here. If it happens in one way, is it possible that it happens in the other way? Okay, so that was what Luis de Broglie was thinking at the time. One call Luis de Broglie, okay? He started considering whether, considering the following. If a wave behaves as a particle or corpuscle, is it possible that a corpuscle behaves as a wave? What are the consequences of that, right? If light behaves as a particle, like in the photoelectric effect, if light, UV radiation, X-ray, and gamma rays behave as a particle, X-rays and gamma rays behave as a particle, like in the photoelectric effect and the Compton effect, the photoelectric and the Compton effect. Is it possible that particles such as an electron behaves as a wave as well? Was doing, okay? De Broglie was doing his PhD thesis, right? And started wondering, right? Wondering the following. Behave as a wave as well. So that's what he started looking. He started looking at these equations here. Linear momentum is h divided by lambda. So he came up with this assumption. So de Broglie came with the following assumption. The assumption that the linear momentum of an electron, the linear momentum of matter in general, had a relation that was similar to that of the photon. This implied that matter must have a specific wavelength, okay, which we call it the de Broglie wavelength, like that. Lambda, right? Like that. Similarly, if a particle is moving with a given velocity, this linear momentum is going to be, its linear momentum is going to be mg. That's what we call the complementary principle. And what we call the complementary principle. 1140, right? And what does it mean by the complementary principle? There you go. The wave and particle models of either matter or radiation complement each other. Okay. By the way, here we have a graduate student writing his PhD thesis, which was just a theoretical exercise in his mind. He put that in his thesis, but didn't perform an experiment because he didn't have the money to do that. Until, this was just, this was just speculation on the part of the Broglie. Until two researchers, C.J. Davison and L.H. Garnier, performed an experiment and confirmed the Broglie assumption. How did they do that? How did they do that? How did they do that? Yeah. Well, they perform the double slit experiment, but not with light. Not with light. They performed the Young double slit experiment, Young's double slit experiment, but not with light, but with a beam of electrons. Okay. When they did that, they observed an interference pattern. Okay. So how do we create a beam of electrons? Okay, I didn't show you that, right? There's a way to create it. There's a very easy way to create a beam of electrons. That's something that people have been doing since the mid-1800s. It's very important, and I'm going to show you one of those videos that we have at YouTube. Beam of electrons. Let's see here. YouTube. Oh, right in here. Electron beam in a magnetic field. Okay. Here you go. I like this one. We have one of those there at LA Harbor. I like to show my students when I do those face-to-face class meetings. Let's take a look. This is something that this device that you're going to see here dates as far back as the 1600s. As the years went by, they start improving on this device until what they have it today. They call it the Crookes tube. Let's see if this video is okay. Okay, here's the Crookes tube. Okay. So I wonder if this is a good video. Oh yeah, this is a good video. That's what I want to show you. Okay, pay attention to this device right in here at his table. Okay, this is a glass tube evacuated. Sometimes they put a little bit of gas there, like helium, but very little. It kept a much lower pressure than the environmental pressure outside. And what you have right in here is a high voltage power supply. Okay, a high voltage power supply. Do you remember that parallel plates that I call the emitter and the collector here? That's exactly what they have in there. The only difference that his power supply is high voltage power supply. Okay, so you have a very high voltage power supply and a device that emits electrons, either this one or the other. Would be more appropriate would be this one. Let's see if we can. Here you go, power supply. Next, I'd like to talk about the math. Let's see. I'm gonna move forward. I don't want to talk about the math because it's not important. Oh, right here. It will send electrons traveling down. Okay, so right here we have one electrode that is emitting. We have two electrodes on each end, right? One electrode is connected to one point of the battery of the high voltage, positive or negative, and the other is connected to the negative or positive. Okay. When you apply a very high voltage, we manage it, and we manage to emit electrons from this tube. Because the beam here is increasing in size, I suspect, I'm quite sure that the electrons are being emitted here from the left side. What we have here is a slit, okay? And we also apply a potential difference between those two ends, so the electrons can fly from one end to the other. That's exactly what we see when we handle something like that. This white screen that you see right here, there's an explanation for this white screen, okay? You don't see electrons by naked eye, okay? You cannot see electrons by naked eye, but you can see the interaction of electrons with something else. That's how we visualize the invisible. That's how we see the invisible. We get the invisible to interact with the visible. What you see right in here is the same phenomenon that you see in the North Pole, the North and South Pole, the northern lights, the southern lights or the northern lights. Okay, that's exactly the same thing. We have charged particles that flying from the sun towards the Earth. They are captured by Earth's magnetic field and they spiral towards the North and South Pole. Why do they spiral toward the North and South Pole? Because the magnetic field of the Earth, they have North and South poles. The magnetic field of the Earth behaves just like a magnetic dipole, with the North and South poles located nearby the geographical pole. Okay, so they call the northern lights. So what is happening here? Electrons are being emitted here in this region. There is an electric potential difference here because there's a very high electric potential difference here. Electrons are accelerated inside this tube. And this white material that you see here is coated with substances, with phosphorescent substances that emits a green color when the electrons strike them. Okay, so that's what this green light is coming from. Electrons that are grazing this surface here interact with this phosphor. This phosphor is the same material that we put in the screens of the old TVs and computers. And they transfer energy to them and produce this green color. Okay, so that's what the other guys, the two guys, Davidson and Germer, were doing. They were using a beam of electrons and they were using a second beam of electrons, just like this one here, passing through a slit with two apertures, and projecting these two beams into a phosphorescent screen, just like this one. And when they did that, they were surprised. They start to see some interference pattern there in the screen. Okay, that was the important experiment that was done. So an interference pattern. So we can do a very simple exercise here for you to have a numeric idea of what you're talking about. We're going to do this exercise and we're going to go for a half hour break, okay? And how can we calculate, calculate the Broglie wavelength of a single electron moving at 1.00 times 10 to the 7 meters per second, which, by the way, is 0.033% the velocity of the speed of the light. Okay. Solution, right? Okay, we're going to use the Broglie wavelength equation. That's nothing but H divided by P. And P is mv. A single electron. Since we're talking about a single electron, we must use the mass of a single electron, right? So here goes 6. Here the Planck's constant is 6.626 times 10 to minus 34 joules seconds. The mass of the electron is 9.1, 10 to minus 31 kilograms times the speed of this electron. It's possible to measure, to find out the speed of the electron whenever you pass it through a difference of potential, right? That was something that we did for in the course of electricity and magnetism. We covered that. Let's put here the multiplication fact sign. Kilograms, and the speed is 10 to the 7 meters per second. When we calculate that, we can do this math. Okay? I'm not going to do the details of this math, but we get something around 72.7 picometers. Okay? That's the order of magnitude of the wavelengths of this electron. So if you can create a slit, a double slit, a double slit, with a separation on the order of picometers, you would be able, well, let's say on the order of 72, right? 100 picometers, right? You would be able, or less, you'd be able to observe, if you can create a double slit or separation of the order of 100 picometer or less, and pass a beam of electrons through this slit, you'd be able to observe a interference pattern with your electron beam. And you don't need 2 electron beams. You can use just one, okay? 1 electron beam. You can, provided, of course, the beam is thick enough to cover the whole slit. Okay? And we can do another exercise, another interesting exercise. Here you go. Here is the Broglie wavelengths. For an electron. What about the Broglie wavelengths for a microscopic object? Microscopic object. Okay, what about? For instance, a rock of 50 grams thrown, right, at a speed of 40 meters per second. That's very fast. 40 meters per second is very fast. Okay? So let's go ahead, do a solution here. Just like before, you know, lambda of this rock. is going to be, I'm going to give you the results. You can do the math yourself, to convince yourself. What we get is not on the picometer range. What we get is far less. I believe we don't even have a name for that. Minus 34 meters. That would be the wavelength of the rock. Okay. So the conclusion is, for you to observe an interference pattern due to this rock, you would have to make it through, right? Through a double slit separated by this distance, 10 to minus 34 meters. 10 to minus 34 meters. That's what you have to do. Obviously, a macroscopic object cannot pass through a slit that's so close. So this is, this would be unrealistic. That's why we do not observe. That is why we do not observe interference patterns from macroscopic objects in our day-to-day life. Okay. And that's 11:57 right now. Any questions? Let's see if I missed any comments here. In the if we knew that waves had particle behavior, why did it take so a long time to connect the idea that light has particle behavior as well? Okay, it has to do with technology. Okay, Raymond, it has to do with technology. Back in the 1600s, for instance, they didn't have the technology that they had in the 1900s and the 20th century. Okay. That's back in the 1600s. Think about that. Today we just go to the electric store and we buy wires, right? Copper wires. We buy light bulbs. We put them together, LEDs and so on. Back in the 1600s, they didn't have that. So it's a matter of the availability of technology, and then there is also the mindset. Okay, there is those two things that play into the discovery in the humankind. Okay. Sometimes you have the technology, right? Sometimes you do have the technology to make discoveries, but you don't manage to make those discoveries because you are thinking the wrong way. The whole society is thinking the wrong way. So that was the great breakthrough that Einstein made. Nobody was thinking like Einstein when he came up with the special theory of relativity. He was a young man when he came up with the idea, but the older folks that came before him, they couldn't have this, they were just tied to their old ideas. They couldn't move away from the old ideas. So there are these two important interplay. First, you have to have the technology. If you have the right state of mind, you'll be able to discover something new. But then sometimes you don't have the technology, even with the right state of mind. Even with the right state of mind. I went through that. Okay, folks, I went through that. When I was working at NASA, I had this idea that nobody believed. And they convinced me that whatever I was proposing didn't work. 30 years later, I'm implementing this idea and everybody else is copying that. So things like that happen. We had the technology 30 years ago to do the experiments I had to do to prove that whatever I was proposing would work. But me and my peers didn't have the right state of mind, didn't have the right mind setting. So that's why it sometimes takes a long time to get those discoveries into the realm of science. Okay. Any more questions? Okay, it's 12 noon right now. That's a good time to stop. Here goes break. Lunch break. lunch break from 12 noon to 12:30 p.m. And I see you in 30 minutes. Oh, okay. He has answered your question, Raymond. Let's see. Like I said, I'm going to repeat here, right? It has to do with technology and has to do with the mind setting. Okay, sometimes you have the technology to make discoveries, but you don't have the proper mind setting because you don't believe what you are supposed to discover. And sometimes you have the right mind setting, but you don't have the technology. Okay, and oftentimes it happens like that. People try to prove a supposition just like the Broglie did, right? He didn't have the technology to prove because he was not an experimentalist. And sometimes, everything matches, okay? You have the right mindset, you have the technology, and bang, right? Einstein had the idea not to think with the mindset at the time. That's right. That's what Einstein, that was the great breakthrough that Einstein made, thinking different from everybody else. Okay, it's amazing how he managed to do that. Okay? And sometimes you don't have the technology and don't have the mindset. You have those four possibilities, right? Sometimes you don't have the technology and don't have the mindset, and that's it. You cannot make discoveries. Okay, so thank you for the question, Raymond, and let's have our break. I stop sharing and okay, so now we're going to do our lab, right? So notes right here. I wrote a little bit here. Raymond's question, right? So sometimes we have technology and the right mindset. That's when we have lots of competition because everyone can do what can be done, right? Everybody knows that whatever needs to be done can be done, right? And sometimes we don't have neither the technology nor the right mindset. Under these conditions, we cannot do anything. What's the point of, right? How can we do anything that if you don't know that it's possible to do that, even if technology in the future becomes available, right? Sometimes we don't have the technology, but we have the right mindset. Under this situation, we can only speculate, which is the case of the Broglie, right? The case of the Broglie. He had the idea, but he didn't know how to do it because he didn't have the technology or the skills, the experimental skills to prove his speculation, his assumption. And sometimes we have the technology, but not the mindset. That was the case of Einstein, okay? There was a technology there, but nobody could see what Einstein was seeing. Einstein even cited an important paper, an important experimental result by Fizeau with an interferometer that Fizeau himself do. Today we celebrate the Michelson interferometers, right? But Michelson interferometer was kind of an evolution from the Fizeau interferometer. The Fizeau did experiments at the time that, according to Einstein, proved the length contraction. Think about that. Someone came up with this experiment in the 1800s. Fizeau himself didn't have the right mindset. He was thinking in terms of the luminiferous ether. And right there, his experimental result for to show special relativity was right there. It was not a negative result like Michelson obtained. That was an important difference between Michelson result that was a negative result and Fizeau's result that was a positive result, which was incorrectly interpreted at the time. So Einstein cited that experiment by Fizeau himself. So we have the technology, but not the mindset, but not the right mindset. Fizeau had the technology, but not the right mindset. He could have discovered special relativity at the time, because he had the actual data. But when we have something like that, it takes time to discover the idea, to discover the important discovery. Okay, that's when, but then there is there's a good advantage on that. That's when you can make breakthroughs on your own without any competition. Nobody's going to try to beat you up for the next discovery, right? And that's what happens to Einstein. Einstein had the right mindset at the time, and so much that it passed years for people to believe in his special theory of relativity. And what I want to do now, we're going to do the Young's experiment. Oh, talking about wave matter, right? Matter that behaves like wave, right? So we're going to come up with the Young experiment. We did those experiments in the past with my students, and it works very nicely. I will start distributing the raw data to you. Let's see here, it's gonna be number 6, right? Lab 6. Let's see if it's this one here before I change anything. Let's see. No, that's not what this one is. This one is the lens. Must be 8, maybe. Okay, that's the one. Okay. Here go displacement. Here's the distance, 2 meters. Oh, almost 2 meters, 1 meter and 0.63. And look at the separation of the slit. The separation of the slit was 0.2 millimeters. 0.2 millimeters. Think about that. 200 microns. Okay, imagine the technology that we have to do that. The technology that allows us to do something like that. Okay, and let's go ahead. That's this one is going to be what I call lab 6, right? I'm going to renumber it. 6. Oh, always happen that. And I will upload it now. Três, 4, 5. Okay, so you have your data sheet there. your spreadsheet. And if that's the one here. Harmonic motion. Give this one the speed of the sound. Okay, Young's double slit experiment. Let me copy everything here. Oh my goodness, why it takes so long? Okay, good. 7, 11, 23. Young's exam is the day after tomorrow, right? Is the day after tomorrow, final exam, right? Final exam. Yeah, the day after tomorrow, all chapters and labs. Remember, I correct the reports for labs 3 and 4 and posted them to your group folder. Posted them to your group folder. Let's take a look there. Let's see, group 4. 1, 2, 3, 4. 4 right in here. 3 and 4. Okay. 3 and 4 HTML files. 1. I want to reorganize that. 3 and 4. Because HTML. 3 and 4. HTML. Everybody should have it there. Everybody should have it there. And going back to my notes. Okay, it doesn't. Now, let's take a look at the syllabus again, right? Okay, 5, 6, and 7 is due the day after tomorrow, so I won't be able to correct them until I get that from you, okay? 5, 6, and 7. So I'll be correcting them after the final exam report for lab 7. Okay, so report for lab 7. What are we going to do for lab 7? Since we are doing lab 7 the day before the exam, I want you to fill up the spreadsheet and upload. You do the spreadsheet during the 2-hour lab, right? 1 hour and a half, 2-hour lab. And once you're done, you upload to your group folder. There will be no need, only the spreadsheet. There will be no need for the hard copy. There will be no need for the hard copy, okay? Make sure you do everything right during the hour and a half, 2-hour activity and upload it the very same day that we perform this activity, which is going to be tomorrow, right? Which is going to be tomorrow. Do 13. Let's see what I'm going to do here. 13. Let me see what I'm going to do here. Yeah. Gosh. Can you turn in 5 and 6 tomorrow? Can you do that? 5 and 6 instead of 13, you know, can you do that? 5, 6, and 7. If you turn in everything tomorrow, I'll be able to correct them before the final. Let's do that. Let me hear from you. There's a problem. Okay. Report for lab 5, 6, and 7. 5, we already did 5. We're doing 6 right now. Gosh, let's see. You know what? Let's stick to the original plan, okay? Let's stick to the original plan. Let's do 5, 6, and 7 for the 13. Report for lab 7 requires only the spreadsheet. There will be no need for the hard copy. But the other two, yes, you need the hard copy. Let's do this way. Okay, and they are all due on the date of the final exam. Okay. Graded. Yes. I don't. You know, the way I do it, Sartak, I look at your hard copies. I don't put a grade there in the hard copies, okay? The grade of the hard copies goes straight in that table of your spreadsheet, okay? I look at your graphs. I look if you put everything nicely there in the graph, if there is no problem with the. So yes, the hard copies have been graded and they are part of that table that is at the end in the spreadsheet, okay? Okay, so okay, we're going to do it this way. There will be no need for well, there's not much change here, right? Will we finish chapter 40 tomorrow? I don't know. I don't think so. It doesn't look like, huh? Let's see. Let's see. Sometimes I don't have time to finish the chapter 40 anyway. But let's see. Well, the priority right now is to do 39, right? I am suspecting that we won't be able to do chapter 40. And if we don't do if you don't cover chapter 40, you know, it will not show up in the exam, okay? So let's see if I can find the book here. Let me take a look. Oh, here you go. Here's the book. Chapter 38, right? That's chapter 38. Oh, chapter 38, they're already getting to Schrödinger equation, huh? And that's what we're doing right now, chapter 38. Let's see what chapter 39 is all about. Energies of attract electron, wave function of attract the electron, finite well, three-dimensional. I'll have to pick and choose here, chapter 39, okay? That's right. That's right. If you don't cover chapter 40, there will be no need to do the homework. Yeah, for this chapter. And 40 properties of atoms. Yeah, I would love to cover that, but I'm suspecting that we won't be able to have. We won't have time for chapter 40. But definitely, we're going to do chapter 39. Chapter 38, chapter 38 is, maybe you won't even be able to do chapter 39 because you still have lots of things to do here. Electron demand, well, let's see how it goes tomorrow. Schrödinger equation, reflection from, okay, here are solutions to the Schrödinger equation. And then I have to look at those ones here. The hydrogen atom is very complicated mathematically, but there is a solution to it. To a three-dimensional electron traps, okay? So we'll talk about that, okay? So we'll talk about that tomorrow. Hopefully we'll be able to cover some of this chapter 39. Sometimes I don't have time to cover hydrogen atom. If you don't have time to cover hydrogen atom, it's very difficult to do chapter 40. But I will inform you the specific sections, okay? That we are covering. So far, we are around here, 38.5 right now, electrons and matter waves. And then we are going to start the Schrödinger equation, which is a postulate of quantum mechanics. This is a postulate of quantum mechanics, okay? We'll be talking about that tomorrow. So let's talk about the experiment right now. Young's double slit experiment. I want to know if I have a, hopefully I have a slide. The Young's double slit experiment. Okay. Final exam is the day after tomorrow at chapters and labs. I correct lab report for lab 3. I've corrected the report for lab 3 and 4. And they are posted, right? And they are posted on your group folder. They were posted. They were posted to your group folder. The report for lab 5. That's let me get that again. Spreadsheet here. Reports for lab 5, 6, and 7, right? Really? Yeah, that's right. My lab instructions in the Kindle book is blank. For which lab are you referring to, Raymond? I'm quite sure there is the Young double slit experiment there. See if you have the Young double slit. Let me check. It's been a long time I don't check this lab report of mine. Lab notes. Well, I'll get to you. Let me check. In this meantime, check the other lab. I believe that there is just one experiment that I didn't post there in the lab in the lab instructions. Okay, check if it's in the other chapter. I'm quite sure that there is some thing in the Young experiment. If it's not, I will look into my own lab manual that I have here in the computer. Lab reports for labs 5, 6, and 7 are due on Monday, 13th, right? 23. Okay. So your lab reports are already renamed. Yeah. Okay.
Also, Professor, I had a question.
Yeah.
So about the homework, it says on the Wiley Plus Canvas that it's gonna be due July 14th at 8:59 p.m. So is that our deadline for our homework?
Yeah, I'll give you an additional. I gave you an additional day to do the homework. Yeah.
Okay, just double checking that that wasn't
Yeah,
a mistake.
I'll give you
Okay,
an
cool. Thank
additional.
you.
But if you want to finish earlier, even better. Right? Do you have a question, Karthika?
Oh no, I'm just checking.
Ah, you just
Making
asked it.
sure I
Okay,
had the
okay,
time
just
to do
ask it.
everything. Thank
Okay.
you.
Okay, you just ask it. Good. Let's see here, and let's take attendance first. Amy hand. Are you there, Amy? Okay, Amy is not answering. I'm gonna put a star here in the name. Alisa?
Here.
Thank you, Alisa. Ashley?
Here.
Thank you. Oh, see, you keep on doing that. I don't know why. Sartak? Thank you, Sartak. Mary? Hello, Mary.
Here.
Thank you. Raymond? Okay, okay, I missed here. Okay, I missed, thank you. Basil. Next is Yeshwan.
I'm here, Professor.
Thank you. Zaid. Okay, thank you, Zaid. Kartika? Kartika just talk to me, right?
Here.
Okay. Sydney?
Here.
Thank you. One more, Sumana. I don't see Sumana here. Okay. Another one is Kyriakos. Are you there, Kyriakos? Okay, thank you, Kyriakos. Andy he. Thank you. Alex Hernandez. Okay, next is Alexis Madrigal Valle.
Here.
Thank you. And what is going to be? 15, okay. Good, the numbers match. And that's the 8th lab meeting, right? Gotta download first. Let's go through this experiment and how it's done. Works very nice, this experiment. Much more fun to do the experiment than to just imagine how the experiment is done. It doesn't look like I have a PowerPoint slide for that. Yeah. Yeah, I don't have a PowerPoint slide for that. Okay, so I gotta just make do with whatever I have here. And okay. Okay, so a young double slit experiment is a classical experiment in wave optics performed in 1801. So look at how many years it went by from 1801 to the 1900s, right? 100 years. And those experiments are closely related to one another, right? Because here we are talking about the wave nature of something that they thought it was corpuscular in nature. And then going to the 1900s, they are inverting the situation, right? What was considered to be a wave also have a corpuscular behavior, also have a particle behavior. What's the historic importance of this experiment? Demonstrate that light behaves as a wave, like a wave. Before then, people thought that light behaved as particles, that light did not exhibit interference effects. Only waves have this type of behavior. Particles do not. They would be able to see some diffraction effect, but they kind of didn't understand exactly what was happening to the light, right? Equipment for this experiment. What we have here, monochromatic and coherent lights. What we use is a laser. Okay, monochromatic. What's a monochromatic wave? Is a wave that has a single wavelength of frequency. And what's coherent light? Is light that emitted at a constant phase difference. So think about your laser beam. There is this region in the laser that you have light that's emitted in there. If the light is not coherent, each of the waves that are emitted from the laser that flies, that moves side by side, because the laser has a small spot, right? Has a finite spot. You know, if the light is coherent, each of those light waves, they would be in phase with each other. In phase means, you know, there is no shift in the phase. Okay, that's what coherent light is all about. No, it's not just in phase, but also has a constant phase difference. To get interference, you must have two or more light sources with a constant phase difference. They can be off phase. Yeah, they can be off phase, but the phase is not changing as time going by. Okay, a double slit, which is two apertures very, very close to one another, and a screen to project the interference pattern. It can be a piece of paper. The screen is at a distance L, and here you go. That's the one I want. Okay. Let's see. I might not have the PowerPoint slides for this one, but at least I have some other illustrations that I can display for you, right? So you have already seen this illustration. Let's see. Might be this one here. Yeah, that's the slit separation. And let's make sure I'm talking to the right wave optics. Yeah. Okay, here you go. That's the slit separation, right? See, that's what it looks like, more or less looks like, for a light ray in which the distance between the slits is very small compared to this distance. Those two light rays, they're almost parallel to each other, almost parallel to each other. And then we're talking about even larger distance than what I am illustrating here. Okay, so we do have the slits like that. And let's go to one of the spreadsheets. I'm gonna keep on moving back and forth here. Okay, here you go. Okay, that's one of the data that I have here. Here you go, the distance to the screen, L, right? L here is almost 3 meters. In this case, it's around 296 centimeters, 292.96 meters. The separation between the slits is 0.2 of a millimeter, 0.2 millimeters. And we are using a wavelength, red wavelengths of red light of wavelength 632. This is a laser. This is a laser. Okay. And what we do, we shine this slit. Remember, it's 0.2 of a millimeter. It's less than the resolution of your ruler. We measure this distance with a microscope. Microscope and a micrometer. That's how we measure this difference. Here you go. Okay, here you go. A microscope. We have a ruler, right, with 1 millimeter resolution, and the separation between the slits is measured with a microscope. A microscope that has a micrometric ruler in the eyepiece. I do not know if you have been exposed to that, but I bought some of those for myself during a project of mine. This micrometric ruler has a resolution similar to your micrometer, 100 of a millimeter, or 5 decimal places for the meter. It's possible to image. Let me show you how a micrometric ruler looks like in the eyepiece of the micrometer, in case you do not know, okay? Micrometric ruler, eyepiece micrometric ruler. For microscope, here you go, for microscope. Okay, a bunch of those here. Let's look at this one here. They look like that. It's something that you put in the focus of your eyepiece, okay? And they have this separation here. You can calibrate them. It's possible to calibrate them, okay? And depending on the magnification that you use, you have to recalibrate, okay? You have to recalibrate the ruler. But, you know, with the regular microscope that we have there at the college, we're getting like 0.01 millimeters of resolution for that micrometric ruler. Looks really nice. Like I said, I have one of those myself. I bought during a project. And so when we measure that, we have this resolution that you must indicate here in the significant figures of the D, okay? Measurement, ruler, micrometer. This wavelength is just the wavelengths provided by the laser. I'm gonna put it here. The wavelengths of the lasers are usually written down on them. And I'm going to increase the significant figures here. You don't have to worry about significant figures of the laser. Okay. And now how do we perform this experiment, right? Huh? Here's the theory, right? This times sine of the dark spots, dark fringes, is equal to m minus half of a wavelength lambda. And we have this approximation for small angles. Okay. The distance here minus this distance here, right? That's what this value is all about. Is this distance minus this distance here? Is the path length difference of each light ray. And if they interfere destructively, we will get this relationship on the right side, whether it's to the left, whether it's upwards, or in this region here. In this experiment, it's far more convenient. The experiment that we perform is far more convenient, works not as in terms of an angle, but in terms of the position. Here is the Y position that's taken with respect to this middle axis. This middle axis here is exactly where the middle bright coincides, okay? And you measure the position with respect to this middle point, okay? There is this relationship, Y divided by L is tangent of theta. And going back to our, that's what we have, right? Y position. And then once you have the Y position, we can convert this value in terms of the tangent. And now you have to tell me whether it's going to be radians or degrees here, okay? I'll let you to figure out on your own. What this angle here? This angle is degrees or radians. So what the data and data that's provided by the equipment, right? Here you go. Data and data that's provided by the equipment manufacturer. Here is also data, and here is the result. Here's the result because we obtained that from existing data. Okay. I'm going to highlight it, data. And then what do we do next? Another student coming in. Amy, okay. So what we're going to do, we want to verify, that's how it looks like, right? The bright spot in the middle. We can say that this dark fringe corresponds to m equal to 0. We can choose either the one to the left or to the right. In this case, I choose the one to the right of the bright spot. The bright spot also has a m equal to 0. I call it n, or n dark, n bright. To the left are negative numbers, to the right are positive numbers. So what do we want to do? We want to plot y of dark in the y-axis and m in the x-axis. And let's not forget, we are getting the dark fringes. Okay? And we made this approximation. We project that in a screen, in a white paper. A screen is a flat surface. And just measure the distance from the bright spot that the y dark is. We measure to this one, to this one, to this one, and we do both negative and positive, right? That's what we have it here. Okay, 0, -1, -2. Ym, because the m is negative, the ym is -2, the theta must be negative. What's the distance? The distance are on the order of 2 centimeters. See that? This is 1 centimeter. This is, wow, 0.4, that's 4 millimeters. This is, they are all measured with the ruler. Okay, this student went too far ahead because he put too many, he couldn't, it's very difficult to measure past the millimeter, okay? But this student did that. And this one is around 2.2. This one is also 2.2. See that? There is a symmetry, almost symmetric. And then what do? We plot. We plot this graph, insert. Remember, there is an approximation here that we're making for the small angles. That's a straight line, add trend line, display equation chart. Let's see what this slope is all about. Y by m. Going back to our theory. Y by m, right in here. Okay, here's my slope. Here, what is supposed to be my intersection. Note, see that the intersection is half the slope. See that? What's theta measured with? Oh, well, I want you to find out, okay? Andy, check their, check their the data and try to figure out what's the unit of the angle theta that you have in there. Okay, and so going back to my spreadsheet, not this one, the other one. I got this slope here, right? I plug it 0.0089, 0.0089, and what do I get? I got a 4% difference. Okay, very close to my theoretical value. Here you go. G, what's G? G is lambda. Yes, you need a sequence figure for the theoretical value. The theoretical value is a function of the measurements, right? So you need a sequence figure for that. You don't need a sequence figure for the slope, but for the theoretical value, yes. The sequence figure of the theoretical value is going to be a function of sequence figures of the G, E, and F. Lambda L over D, right? Or lambda D over L. Let's see, lambda D over L must be lambda D over L. Yeah? No, lambda L over D. Okay, lambda L over D. That's what this slope is all about. take and then you can set the intercept as well. Let's see if the intercept is a good one. 0.004. Don't forget to put the negative sign. 0.004. I'm getting 6%. Let me see if you can do better than that. I can increase the number of decimal places there. Format trend line label. Oh, 396, right? Is minus 0.00396. 7%, a little bit more than that approximation that I made. So these are actual data that my students got. Let me undo everything that I'm doing here. I don't want to save this guy, modified version of this spreadsheet, right? So you know what to do, right? So start working in there and let's see how you're doing. Measures the ruler, measures the microscope micrometer. No, you don't need to do that. Download the spreadsheet, plot Y versus M, which is the order number. In that slide, I call it in. Log the slope in its respective table. Log the slope and intercept the slope and the intercept in their respective cells. In their respective cells, like that. Logging the units. What's YM measured in? Okay, so let's take a look here. Well, what the unit do we use for lengths, right? YM is length. What's the unit that we use for lengths here in this lab? They call, okay. Think about that. We are measuring Y sub M with the ruler, okay? Here's this M, here is not meters, right? Here's M, here is the odd number. Okay, can you figure that out, Alexis? With this little hint? The Y, okay, good. So we're measuring, let's put here what we are measuring here. What are we measuring here? One, the L, distance from the slit to the screen, and we measure that with a meter stick. Resolution x.123 meters. L. Okay. The slit separation with the microscope slide. Microscope micrometer slide with a resolution of 1, 2, 3, 1, 2, just like your regular micrometer. Okay. Everything is measured in terms of meter, unless the student log it incorrectly there in your spreadsheet. Okay, Alexis? Unless the student measures put the numerical value in the incorrect unit. Okay, the distance of the dark fringe from the bright spot in the middle. That's Y sub M, right? That's measured with the ruler. Measure is the ruler. The ruler in the 1, 2, 3 meters. from the dark spot in the middle, the bright, the bright spot. Yeah. Measure with the ruler. What else? Let's go back to our LD, lambda. We don't measure lambda. We don't measure lambda, right? We don't measure lambda. Lambda is provided by the manufacturer, by the laser manufacturer, by the laser manufacturer. So let's put that at the top. What's not measured, you put that at the top. The slit separation, let's see. Yeah, okay. The distance, the slit separation D. Is there anything else? Oh, we measure the M as well, right? The order of the dark and bright fringes, M. Measure, we count them. In a way, we count them, but they don't have significant digits in this case because their M are integer numbers. Okay, so go ahead, start working there. You have plenty of work to do, right? Download the spreadsheet, plot Y versus M, log the slope and the intercept in their respective cells, display the proper number of significant figures, work on the CL table. Okay, I'm gonna save this one here. Let's see how you're all doing. You're all doing, let's see here. 123. Amy, did you download the spreadsheet? Yes. Did you plot the graph as well? Yes, good. So I want to know the percentage difference that you got for the slope and the percentage difference for the intercept. Okay, did you already got the percentage difference for the slope and the intercept? It's okay if you didn't if you didn't got it. Oh, you got it already. Okay, 4.36 is for the slope, 6.19 is the intercept, right? So let's go for, thank you, Amy. Let's go for Alisa. Did you download the spreadsheet? Alisa? Yeah, good.
Yeah.
Okay, did you plot that too? The graph?
Yeah.
Did you get the same percentage difference as IB got?
Yeah. I think we're done with everything.
Huh? I didn't
I
understand.
think we're finished with
Oh, you
everything.
already finished? Okay.
Yeah.
Okay, so let's see here. So what else do we have here? After that, you have to worry about units, right? From the units, you go for the sig pick, and then the last one is the CL. So you're done with everything, right? Let me put it here. Done. Let me see with the other groups in your. Okay, so you're done. Does apply for IME as well, IME? Did you do everything? Yes, okay. So let's go here. Let me check Ashley. Ashley, did you download everything?
Yeah.
Plot that too. Are you done? Like the other group members?
Oh, yeah, we're done with everything.
Oh boy, too easy, right? Yeah. I gotta do that more difficult. So you don't go early home. Okay, if you wanna go, you can go and get ready to turn in the spreadsheet. Let's see, Tartak. Tartak, did you download the spreadsheet? Yes, it's slope plot is slope 2.4, 4.34, and you're done, huh? Okay, let me check with your other group members. Mary, are you there? Wait, you put it backwards. Okay, wait, you put. I don't understand. Wait, you put it backwards. I don't understand what you mean. I'm sorry. I slope. Okay. You put. Okay. So you mean I see. Yeah. Okay. I put this before the intercept, right? I didn't notice that. Good point. Okay. So Mary, let's see. You downloaded, right, Mary? Did you plot the graph? Yes. Percentage difference. Is it the same as Sartak? Yes. Okay. Next, you finished the units already? Units, CL, and sig fix? Yes. Okay. Let's see another student here. If Raymond, are you done as well, Raymond? Yeah. Okay. So if you folks want to leave, oops. If you folks want to leave, you can go. Basilio, how are you doing there? Did you download everything?
Yes.
Okay. Plot. Did you plot it?
Yes.
Okay. What's the percentage difference for the intercept and the slope?
I'm still trying to arrange it. I'm trying to make sure I'm getting everything correct. I just wanted to know,
Huh?
can I see your graph real quick just to make sure I plotted it correctly? Because sometimes I know we have to, if you plot it in the X or the Y.
Yeah. There's no error here. There's no way to plot incorrectly, okay? Because whatever is to the right ends up in the vertical, in the y-axis, or
Oh, okay.
on the left. So there's, whatever you plotted, unless you do something right to the graph.
Oh yeah, that's what I got. Cool.
Okay. So that's the plot, right? And you're working did you work on this units already or not yet, right?
No, not yet. I'm still,
Okay.
yeah, I just plotted it right now. So now I'm gonna do the CL and then I'll do the units after.
Okay, good. So Joshua, did you download and plot your graph?
I finished everything. I only have one question.
Yeah. Before we go there, tell me what's the percentage difference on the slope and the intercept, please.
Okay, so I had 3.55%.
Okay, and the other one?
I think it's sorry. Negative 12%.
Okay, that's kind of high. Okay,
Oh.
that's all it is. Huh? So you finish everything. Let's see. Okay, so what's the question you have?
What was the units for theta? Is it degrees or radians?
I want you to figure that out on your own. Okay,
Okay.
there's a way to take a look, right?
Yeah.
Look how I wrote down the equation, right? So you might want to test. For instance, you go. I'm gonna put arc.
Oh.
You go
Okay.
arc sine. Let's see, sine of 1, right? You know
Yeah.
that sine of 1 is 90 degrees, right?
Yes.
Okay, does it give you 90 degrees?
That is in radians. Okay.
Yeah, so if you want to change to degrees, you have to apply the function degrees here to this
Oh, okay.
value. So the actual, the most realistic, the most useful measurement of angle is the radians. It's just
Yeah.
that you are educated to think in terms of degrees. Okay,
Mm,
it's like we're educated, and there's a reason. There's a historical reason for that. Why do you use degrees instead of radians? The radians is the most useful measurement, is the actual physical measurement, right? The reason we use degrees has to do with the Babylonians.
oh,
Why is that? What does it have to do with the Babylonians? Okay, the Babylonians, they thought that the year was 360 days. They thought their calendar was 360 days. So for every day in the year would correspond 1 degree of motion of, let's say, the sun around the earth. Okay, that's why we ended up using degrees. It has to do with the calendar that the Babylonians used to use. They didn't have a calendar of 365 days. They had a calendar of 360 days. And then every now and then they would adjust their calendar to be synchronized with the position of the sun. Okay, so that's where it comes from. That's where the degrees come from. How to check the grade of the lab? All you have to do is to open that HTML file that I uploaded to your folder, Alexis. Okay, if you do not know how to open it, let me know. I believe we did that in one of the classes in the past. Okay, and I have the notes there, also explaining step by step how to open that HTML file. If you want to stay after the class, I can walk you through. Okay, Alexis? So let's see the next one, right? And Zaid, did you download your spreadsheet? Yes, okay, good. Did you plot the graph? Yes, okay. What's the percentage difference? Did you get the same percentage difference here as Jeshwan? Same, okay, good. So what about the rest? Did you do everything else or you're still working on something? I'm done. Okay, so help Basilio before you go. Okay, since you're in the same group. Basilio is still working on the other thing. So help him before you folks go. And then whenever you all done, let me know. Let's go to Karthika now. Karthika, are you there?
Yes. I'm still working on it right now, actually, just because I'm having an internet problem and I can't download a lot of the files.
So what are you working on right now?
I'm figuring out how to fix my internet.
Oh gosh, you didn't download the spreadsheet yet?
My phone.
Okay, so I'm gonna put it here, downloaded, working on that. Okay, Sydney? Okay, are you there, Sydney? So before you go, Kyriakos, let me see. You're done, right? What's the percentage difference you have got? 0.9. Okay, that should be 0.9. I presume is the slope, and the other one is 7.37, right? I want to have that. Okay, let me copy and paste here, and I'll go to the other student. Okay, ideally you should stay here to help your group members. Okay, but if you have to go, okay, I'll let you go. Suman is not here, right? Suman is not here. And we are left with Sydney. Are you there, Sydney? Yeah, I don't want to see. Sydney is here, but looks like she's away from the computer. I will put a star here in her attendance. Next is Andy. Hi, Andy. Andy here. Andy, we're done with everything except for the unit. Okay. Okay, so working on the unit. Everybody or just you? Everybody's done in your group or just you? No question. Okay, before your question, what's the percentage difference you're getting, please? Point for the slope, right? And what about for the intercept? 2%. Okay, so what's your question? How do we figure out the unit for I? For I or for lambda? Are you referring to lambda? On our spreadsheet. Okay, so if your spreadsheet is it located here in this first table? Is it in red color G4? Yeah, that's lambda. That's the wavelengths. Okay. So the wavelengths. Okay, now you should know what's the unit for the wavelengths, right? And you're doing everything in the international system of units. Note, see that this value here is 10 to minus 7, right? So you should know now. Okay, so it's Andy. So you did everything. The only thing you didn't do was the units. Now, what about Alex Hernandez? Are you there, Alex? Oh, out of our group, okay. But I still want to see whether Alex is still here or he moved away. Okay, same. We're working on the same sheet. Okay, on the same sheet. Okay, good. And let's go for Alexis. Right? Just tell me that you are here, Alexis. I know that you're good.
I'm here.
You're here. Okay, good. So, any questions, Alexis?
I'm good, thank you.
Okay. So that's now we're left with Sydney and Basilio, right? Who else? Yeah, Basilio and Sydney. Well, Karsika too, right? Karsika that's trying to figure out how to get the internet going there. Do you have any questions, Basilio?
Nope, we just finished it.
Just finished? Okay. So it should be here. Okay, and now Karsika must be busy fixing the internet there, right?
Yeah.
Okay, what about Sydney? What happened to Sydney? Okay. Okay, so just two students, right? They're left here. Okay, if you have a question, let me know. I'll be here. That we have what, another 20 minutes here, and then have the break, half an hour break. Half an hour break? No, we have a 1 hour office hours. Okay. I stop sharing my screen.